Hey everybody, my name's Jacob and welcome to the Junior Chemistry Course 1. This course is for primary age students and there's a fantastic booklet available on Tiny Science Lab, and hopefully you'll have a Junior Chemistry Set 1, which is required for this course. And we're going to have a lot of fun doing chemistry together. And chemistry is exploring how substances combine and react together to make new substances. And, you know, chemistry is so important for getting our food and for farming and for growing things and for making things. It pervades all aspects of our society. And it's really interesting as well. And that's why I love chemistry. So, in today's lesson, we're going to be exploring the components of the chemistry set, and we're going to be looking at what they're used for, and we're also going to be labeling the equipment and drawing the equipment as well. So strap yourselves in, because let's get into this junior chemistry course. So let's open the hinge and then reveal the treasures inside. So, a very important piece of equipment is the thermometer. The thermometer. Now, I might just put this booklet down over here, and I've got a nice clear workbench. Very important to keep things nice and tidy. Now, a thermometer tells the temperature. When you use the thermometer, see that silver thing on the end? That's the probe. I don't touch that with my fingers unless I'm measuring the temperature of my fingers. And so let's do that. How about you hold the probe in your fingers and you should be able to see the numbers going up. So at the moment, the temperature is 28.8. What about yours? Oh, now it's 29.8, 30.5 degrees Celsius, 30.9 degrees Celsius. I wonder what it will go up to. Probably will go up to about 33 degrees, something like that. Now, this lead can actually go in hot water, it can go in the freezer, but don't put this part in the water because it will probably not work anymore. So, but this part can go in water, no problem at all. And when the batteries eventually go flat, you can actually replace them. Okay, so this has got replaceable batteries in. Now, to put it away, you get two fingers like this, and you wrap the lead around your two fingers, not too tight because we don't want to cut off the blood circulation. And also we need to be able to pull your fingers out because we don't want to have to lock your fingers away for, you know, till we use it again next time. And then push that lead into the hole like that. And then you can push the thermometer down nice and firmly on top, and if you push it down, I don't push it on the screen, by the way, I actually push it by the sides of the thermometer. That way I won't break the thermometer. So, my next favourite piece of equipment, it's actually two of them. There's two 10ml beakers, okay, two 10ml glass beakers. Be careful with these, because if they drop onto the floor, they'll probably break. So, this is very special equipment, and we have to look after it. It can be dropped a little tiny bit, but not too much, because yeah, it might shatter. And broken glass is very sharp. And so one thing that you should check when you open up the container is to see whether there's any broken glass. Now, don't fret too much if there is. Just get an adult to remove it carefully, because Tiny Science Lab does sell the spare parts for this set. Okay, so if you break one part, you can actually just buy a new part, so you don't have to worry too much. Now, I'm going to keep holding one of these in my hand because another favourite piece of equipment of mine is the stirring rod. And this is a glass stirring rod, and it's for stirring, not banging. If you bang, you'll probably poke a hole straight through your beaker, and that's not very good at all. So very good for stirring. So beakers, good for holding liquids and powders. Not so good for holding like solids. You can hold some solids. So later on we're going to be putting Orbeez in here. You could put some sand in here or rice. but I wouldn't put big rocks in here. No. I put like citric acid and bicarb soda, but yeah, nothing too big and lumpy. So let's pop this away. The safest place for your equipment is in the beautiful foam pouch. And under the stirring rod is the pipette. Now the pipette's it's got a bulb on it which you can squeeze. It's got a flexible bulb which you're squeezing, and that can actually draw up liquid. So you draw up liquid with this pipette, and then you can transfer it from one place to another. Sometimes they're called transfer pipettes. So I'll pop him back. Tiny spoon. Now, poor Barbie, I can hear her crying. That's because we've got all Barbie soup spoons. I believe this is a 0.25 milliliter spoon, parents, so a quarter of a mil. So you'd need 4 of these to have 1 mil of water, 4 scoops of these. And it's got a beautiful shape, doesn't it? And it's quite robust and easy to clean. The tiny spoon will be a very important part of our explorations. Then, a little bit tricky to remove, but there's a plastic container, and the plastic container's got a lid on it, and if you go left or anti-clockwise, lefty-loosey I say, and righty-tighty, so lefty-loosey, then we can open it up, and the first thing I notice is that there's a little disc, a little wooden disc, and that's got our brand on it, and then there's 2 metal pans, okay? Now, if you look carefully, you'll notice that they are actually different types of metal. One's more shiny than the other. Now, most metals are shiny, and one's actually a little bit heavier than the other one. The one that's very, very shiny, well, that's actually steel. And you can tell that because if you pull out the magnet, okay, there's a magnet here that's got blue and red on it. Now, although this is not made out of glass, you don't want to drop the magnet because it could actually shatter. But have a look. If I go onto one of the dishes, nothing happens. Oh! But if I go onto the other one, it attracts it. Whoa, look at that. Because that's got a lot of iron in it. And iron is a magnetic metal. Okay, so the one that's magnetic is a steel pan, and the one that's not magnetic is an aluminium pan. And so I can put the wooden disc back on, I can put the magnet back, and I can screw the lid on righty-tighty. Oh, but underneath there's something else. What is it? It's a little plate. A little white resin / plastic plate. Poor Barbie, she's missing her dinner plates as well now. Very good for putting powders on. You can even put some liquids on here. Very good. You could put some like tiny little leaves or little flowers, or it's very useful, a nice white plate like that. So we'll pop in there and push that plastic container back in. And next to it is the conical flask with a rubber stopper lid. So the rubber stopper actually can get pushed down into it and forms a very good seal because you can actually trap some gases. You can trap some gases in this conical flask. And very good for holding liquids. Yeah, wonderful piece of equipment. And sometimes you might even put the funnel in the top of it because the funnel is very good at directing liquids, transferring liquids. And if there's some filter paper in here, you can actually filter the liquid that's going into the large conical flask. So we've got a funnel and we've got a conical flask. And let me pop these back in like that. Lovely. Back into its little home. I like it. Next to that is a little vial. Now it's a little plastic vial and it's got a lid that goes pop when you pull it off. And the vial is, you can store some things in here. You could store Orbeez, or you could store some powders or some little treasures, whatever. It's good for storing things. And so I'll just put the lid back on and pop him there. So that's a quick introduction to all the pieces. How about we now label the set and put the names down for each piece of equipment? Good idea? Yeah, I think so. Great idea. Let's go. Okay, so I've got a wonderful overhead camera so that you'll be able to see the labels as I write them. So here we've got our thermometer, and a thermometer measures temperature. Thermo, that means heat, and meter means to measure something. So thermometer. Next to it is our tiny spoon. Our tiny, that means very small, spoon. Tiny spoon. And underneath the tiny spoon is the plastic container. So plastic with a C on the end, and then a container like so. And then next to the plastic container is the funnel. Okay, it's the funnel. Funnel. And just between the funnel and the plastic container is the stopper. Okay, the stopper. Now it's a rubber stopper, but we'll just put stopper. And the stopper is actually attached to the conical flask. And so I'm going to write the two words on top of each other. Conical up here, and then flask underneath. Perfect. And then here underneath the plastic container is the magnet. So we've got the magnet. There's the magnet there. And next to the magnet is the vial. V-I-A-L. Now let's come over to the other side, and we've got a beaker. In fact, there's two beakers there, isn't there? Two 10ml beakers. And underneath the beaker is a stirring rod. Now, I can't write stirring rod there, so I'm going to write the word stirring up a little bit higher, and then write the word rod under it. And then our last thing to label is the pipette. Okay, the last thing to label is the pipette. There we go. That's the equipment labeled. And so now I'm going to show you how to draw the equipment. So I'll just move this up here, and you'll need a ruler and a pencil. Now I'm going to be using a pen so that you can see it quite clearly. So the thermometer, I can't draw it 1-to-1 scale because that just won't quite fit, but I can draw it fairly closely. Now in science, we draw very simple drawings, 2-dimensional. They don't have to be 3-dimensional drawings, so we keep things very, very simple. And so I'll just draw a rectangular box, just like that. And I like using a transparent or a clear ruler because that actually helps me see the lines. And then I'll put the numbers here. 20.6 degrees Celsius. And of course, its purpose is to measure temperature. Of course it is, temperature. Next to that is the spoon. So we've got a spoon here. And the spoon is pretty similar in length to the thermometer. So I'm going to draw it very similar in length to the thermometer, and a very simple drawing, just a line with a scoop on it. It's that easy, okay? It's that easy. And so we can say scooping solids. Scooping solids. Perfect. The funnel. Now the funnel is a little bit wider than half of the thermometer and about double its height. So I'm going to actually start at the bottom. Okay, it's actually, I find it a little bit easier if I start at the bottom and go up. And that looks about right. That's a good angle. And I want to try and get the same angle. Oh, very good. And so notice the top doesn't have a line because there's no, it's open. And so I have to draw it open, leave it open. And the bottom is open as well. And so the bottom is open there. And so it's good for transferring liquids. and also for filtering. Filtering. So I'll put and filtering. The resin plate. The resin plate. It's a little bit wider than half of the thermometer, and so it's also very simple to draw. Just like that, a line and then two little lines here for the rim. And you can hold powders and liquids, holds, powders, lots of chemical powders and liquids. So that's the first page of the introducing the equipment done. And so now let's do the second page. The aluminium pan. The aluminium pan. Now it is very similar in size to the funnel. So I need to have it in proportion. Okay, I need to have it in proportion. And so the aluminium pan is about like that. And I can put the edges on it. And so it's also good for holding liquids. Okay, holding liquids, as is the steel pan. Now the steel pan will look almost identical. The steel pan will look almost identical. So a line across the same width, and again we can go holding liquids. Perfect. Here comes the beaker. Here comes the beaker, and I'm going to compare the beaker to the pan, and notice it's the same diameter as the pan. And so when I do my drawing, I do the same diameter as the pan, which is about that. And then I can do my sides, and that is the beaker. Perfect. Notice that it's open up the top, and we'll put stores / holds liquids and powders as well. Very multifunctional. The magnet. Let me just compare the magnet is actually the same length as the height of the beaker. So it needs to be a bit wider than the base here of the beaker. So that's about the magnet. And the magnet's got an N and an S on it. An N and an S. That stands for north and south. And so we can do explore magnetism. Explore magnetism with our magnet. Oh, the rubber stopper. Hey, I love the rubber stopper. The rubber stopper, it's got a narrow base that goes up to a wider top. There we go. A narrow base that goes up to a wider top. Perfect. And that's for that's like for a sealing the conical flask. That's a good word. Sealing the conical flask. Excellent. The conical flask itself. Look, there's a nice big room there to draw it, and it's got a very similar. It's got a very similar diameter at the base to the beaker. So that will help draw it in proportion. And again, I like to start near the bottom. And so the base is similar in diameter to the beaker. And then it goes up like that. And then a similar angle and similar height on the other side. And goes up to a neck. Perfect. Excellent. And that's great for storing liquids and gases. Liquids and gases. If you put a rubber stopper on it, you can actually store gases in there. The vial, well, I have to draw that sideways. Okay, the vial I draw sideways because it won't be able to fit vertically. Very simple. Now it's actually closed at this end and it's got a lid on it, so I can put the lid like that, and I might just hash the lid, and it's good for storing substances. I'm not going to say what substances, you can decide. Solid, liquids, gases, whatever. The wooden disc I might actually just use the wooden disc itself to draw it. So I can trace around the wooden disc. See that? Hey, that was a good idea. I can even write Tiny Science Lab on it. Tiny Science Lab, and draw the what is it? A conical flask. There we go. Wooden disc. Oh, what's it for? It's for branding. It's actually for branding our company. So, excellent. And then the stirring rod. Be careful with stirring rods. We don't want them to fall on the ground. And you can see that I've made this cell really quite long so that we can fit him in. And there we go. And surprise, surprise, do you know what it's for? Stirring. There we go. Stirring. And the pipette, the pipette is actually the longest of the pieces of equipment. And so, zoop. And zoop, like that. Did you do that sound effect? And if we go like that, now I'm drawing the bulb, and I have to go around like that. There we go. Amazing, and that's for transferring liquid. Transferring liquid. All right, well, I promise that was probably the most boring of all the lessons coming up, okay? So hang in there. I'm really, really sorry if you found that really, really boring, but I can tell you that now that we've done that, from now on, when I refer to any of the pieces of equipment, you'll be able to say, oh yeah, I know that one, and I know that one, and I know what to do with it, okay? So we will be exploring the pieces more as we use them, but I can tell you from now on, things are going to be far more exciting. Thanks for hanging in there, and thanks for coming along to this lesson, and I look forward to seeing you next lesson. Bye for now, everybody. Bye, 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 bye. Hey everybody, in this lesson we're going to be looking at classification. Now classification is grouping objects or animals or plants or things or whatever according to particular properties that they have in common. And we're going to be classifying the bits of equipment in your Junior Chemistry Set 1. Now for this lesson, you'll need your Junior Chemistry Set 1, of course, and a bowl with water. Now, my bowl's made out of glass, but you can have a bowl that's made out of whatever you like. It could even be an ice cream container. So, we are first going to classify the pieces of equipment according to the material from what they're made. Now, some of these pieces of equipment are made from glass. And glass, oh, here's an example of a drinking glass. Look at this. This particular one is transparent. You can actually see the light that comes through it. I can see straight through it. Glass is quite brittle. You don't want to tap a glass too hard on the table, do you? And you certainly, don't want to drop it on the ground, because you know that glass is very brittle and it will break. Now, the formula for glass is silicon dioxide. It's actually very similar to sand. In fact, that's where the first glass was made, when lightning struck the desert sand and left glass behind. You melt sand and basically you can end up with glass. How good's that? What else is made from glass? Well, here's a smaller glass. Oh, here's a glass jar. So glass jar with it's got a metal lid on it, and this one's actually got some coconut oil in here. Smells like I'm on holidays. Oh, we've also got a light globe. Now, sometimes when you have a good idea, ding! You have a light globe moment. Now, this glass is not transparent, it's translucent. It lets some light through, but not all the light. That's why it appears white. Now you don't want to drop this. It's got very, very thin glass and it will break. So what are some of the components or pieces in our sets that are made out of glass. Do you want to get one out? Let's see if you get the same one out that I get. Ready? Okay. I've got the glass beaker out. Is that the one that you pulled out? And I love them because, you know, you can see through them. They're very rigid. They're easy to clean, but don't drop them on the concrete floor. Otherwise, your set will be incomplete and you'll have to buy a new beaker from us. But anyway, isn't it lovely? Now we have to check to make sure it's not broken, because broken glass can be quite sharp. So I always just check to make sure that there's no broken pieces in my set before I put my fingers in there and pull them out, because that might cut you. All right? So just be careful of broken glass. So the beaker is glass. What else is glass in here? Oh, what are you getting out? Oh, I've got out the glass stirring rod. The glass stirring rod. And this is probably one of my favourite pieces of equipment as well. It's very rigid, which makes it very good for stirring. Imagine if it was made out of like rubber. When you tried to stir it, it would just like bend all over the place. That wouldn't be very good. It's very easy to clean, which is one reason that I like it. Now, you can see through it, sort of. If you put it to your eyes, you can actually see some very interesting things going on. But we don't make the stirring rod out of glass so that you can see through it. We make it out of glass so that it's easy to clean and because it's rigid. Is there anything else that's made out of glass in here? Absolutely. There's a glass conical flask. Well, this thing on top, that's not glass. That's made out of something else. We'll talk about that later. In fact, yeah, we will. And so the glass conical flask, look, it's shaped a little bit like an ice cream, isn't it? So that's the items that are made out of glass. Now, plastic. Plastic. Lots of things in this world are made out of plastic, aren't they? Well, for example, these safety glasses are actually made out of a plastic. All right, this plastic you can actually see through quite well. The pieces that go over your ears, though, they're coloured orange and you can't see through them. That lets a little bit of light through. So we've got transparent and we've got translucent. Not in your sets, but is a little 20mm plastic cup. Now, it's sort of like hazy. It's not that, I don't think it's that nice. I don't actually like plastic little cups and that sort of thing because they scratch easy, they don't clean that easy, so that's made out of plastic. Oh, I see something else. When I built my deck, I needed some screws and they came in a plastic container. And again, it scratches up and it becomes quite hazy, but it's fairly strong, but not super strong because look, it's got a bad crack in here, but I can still use it even though it's cracked. It's got a little bit of flexibility to it. Now, talking about that, here's a wash bottle. And our wash bottles are made from plastic. And if I squirt it, if I squeeze it, the water comes out. Now, if this was made from glass, you wouldn't be able to squeeze it, would you? It's very important that it's made out of plastic so that it is flexible. So plastic can be very good, but plastic is made from crude oil, which is one reason why it's quite cheap, because we can actually get a lot of crude oil out of the ground from under the oceans, and with some processing we can produce plastics. Now, one of the downside is that we probably use too much of this plastic and that we don't reuse it, we just sort of like throw it out, and that's not very good at all, is it? Now, our containers are made from plastic. That means that we can see through them. They're relatively cheap for us to buy, but they're still strong enough for what they need to do. Now, what are some of the things in here that are made out of plastic? Well, we've got a plastic funnel. Okay, we've got a plastic funnel, and it's got a little bit of flexibility, and you don't need to see through it, and so it's not so important that it's transparent. This one is actually translucent, and it's okay if it gets a little bit scratched. And because you don't use it, you won't be using it that much. It's not that, we don't have to worry about washing it too much. The plastic vial. The plastic vial with the lid, which if you wiggle, you can pull the lid off and get a little bit of a pop. Now, you wouldn't worry about dropping this, would you? Because you know that plastic is quite flexible and it's not going to break easy. It's not brittle like glass. And so plastic, okay, is very, very good for making something like this. So that's the vial. Oh, talking about flexibility, the pipette is made from plastic, and it's very important to be made from plastic so that you can squeeze it. If this was made from glass, you wouldn't be able to squeeze it and you wouldn't be able to get liquid up into it. So if I get some liquid out of the bowl and give it a squeeze, woo! See that? You can squeeze the liquid out. So pipettes, very, very good and pretty good to clean as well, to be honest. This plastic is actually not too bad to clean. Oh, there is actually a fair few things that are made from plastic in this. This one here is a very rigid plastic. Okay, I actually think it's a type of polystyrene, this container with the lid on. One of the beauties is that it is quite transparent. Okay, it is quite transparent. You can actually see through it. It's a very rigid plastic. It means that it's not very flexible. It's quite hard. But yes, this container is made from plastic. Oh, and under it, oh, do you know what that is? Oh, Barbie's dinner plate. She's looking around for all the dinner plates, but we've got them all. Anyway, Barbie's dinner plate, or the plastic resin plate, is made out of plastic as well. Oh dear. You're probably thinking, why have they sold me all this plastic stuff? Oh, there is some glass in there, so don't panic. Oh, we've got a plastic spoon, okay, like this. Now, we used to sell these sets with metal spoons, but I'll tell you a little bit of a secret. The metal spoons, after maybe a year or two, started corroding, and that meant they weren't able to perform their functions. And so we've actually replaced the metal spoons now with plastic. So there we go, the plastic spoon. And the thermometer. Okay, the thermometer is actually some plastic too. We 3D print the case from PLA. That's a type of plastic. This type of plastic actually is biodegradable. That after, I think, 10 years in the ground or something, it will actually degrade away. And there's actually a plastic coating on the lead. And that is all for the plastic in our sets. Metal. Okay, metal. Well, let's have a look at some different metals. Have you ever been to Japan before? I've been to Japan. And they've got lots of vending machines. And they love drinking coffee over in Japan. And this one is a Kilimanjaro blend, and it's made out of steel. It's a steel can. It's actually quite heavy. This one here is an iced coffee that's made out of aluminium. It's actually quite light. This one here, this is a drink, but do you know what type of drink? It's a creme brulee drink. It's like, it's really quite thick and very unusual, but it tastes very, very nice. I know you're saying, oh, I want to try some of those drinks. Well, you'd have to go to Japan, I guess. So they're made out of metal, and metal's strong, but it's actually got some flexibility in it. So you wouldn't worry about dropping these, would you? Because you know that they're not going to break. They'll just flex. Now, what else is made out of metal? Well, lots of our window frames and components in buildings are made from aluminium. Okay, it's quite strong, and aluminium is actually used in aeroplanes as well. Quite strong, but not brittle. It's not brittle. You can actually stretch it if you apply big enough force. And in your house, you probably, you need some water. And so we have water pipes that are made from copper, and it's strong, it doesn't tank the water, but it's got a bit of flexibility as well. So if your house moves a little bit, it won't break that. Imagine if this was a glass tube and you put it against your wall and your house moved a little bit, it would just break, wouldn't it? I should have brought some electrical wiring because that's made out of metal as well. But what in our set is made out of metal? Well, I can tell you that inside, the end of that probe. The end of that probe is made out of metal. It's got a metal cap on it. So the probe for the thermometer is made out of metal. And in fact, the wiring inside this wire is actually metal. It's probably copper. And there's actually some batteries in here that are metal and others components. So you might just want to put down parts of the thermometer, and the thermometer probe into the table. That's fine. Is there anything else that's metal in here? Absolutely there is. Well, let me just put this away neatly. It's important to put away your equipment neatly, okay? Inside this plastic container, if I get it out, there's two metal pans. One's, well, they're both silvery. One's a little bit more grey than the other. And one is aluminium and one is steel, okay? Now, if you get your magnet out, this is your magnet here. It's got an N for north and S for south. Then you'll see that one of the plates is magnetic. That's the steel plate. So that's the steel plate, and it's mainly made out of the element iron. So probably about 98% iron and about 2% carbon. That is an alloy called steel. Now, if you add a few other things like vanadium and chromium, then it's stainless steel. But the aluminium, well, that's just made out of pure aluminium. That's an element, and it's not magnetic. So you've got the steel pan is metal, aluminium pan is metal, and in actual fact, the magnet is metal as well. All right. It's interesting how I've seen how they make this. They actually have powdered metal. It's a powder with a glue in it, and they can put it in a mold and they compress it, and then they magnetize it after. So how many things have we've got? About 4 or 5 things that are metallic. Oh, I forgot to put this disc in there. Now rubber. Now I've spent all morning making this special skateboard for you. Okay, oh, look at this. It took me hours. Little Lego man on a scooter. Now the Lego is plastic, but the tires, okay, they're like very, very flexible. You'd say they're rubbery. Well, they're rubbery because they're made from rubber. And rubber actually originates from the rubber tree. It starts off as a white sap, which is collected, and then you add some chemicals and you heat it up, and it turns into quite a fairly rigid material that's got some flex. So there's some rubber there. What about your bike tires or your car tires? They're made out of rubber as well. And there's one thing in this set that's made out of rubber, and it is the rubber stopper. So, well, you certainly wouldn't worry about dropping that on the concrete floor because you know it will bounce and it won't break. And the flexibility is very good because it means you can push it in. You can push it into the glass conical flask. So, and it sort of like wedges itself in. If that was a piece of glass, you wouldn't be able to like push it in, would you? You know, it just wouldn't flex, it wouldn't move, so it would not be very good at all. So that's our rubber. And that's all for the rubber of, oh no, you could probably say that the foam is rubbery. So the foam infill is quite rubbery. So maybe put the foam infill. Now I've got a question for you. What is brown and sticky? Are you thinking a stick? I hope so. Because a stick is made from wood. And this stick, to be honest, is probably just good for starting a fire. It's so small. Or for a termite. Be a nice termite meal, wouldn't it? Termites like to eat wood. But what other sort of wood do we have? Well, if you have a pine tree and you cut it down and you mill it up, you get some wood, which we call timber, because timber is processed wood ready for building. And this is a very common building material in Australia, okay? Pine, and it's got some chemicals in it to stop the termites from eating it. The termites go, no, I'm not going to eat that one. So, this cedar blind, okay? Cedar is a beautiful timber. Smells very, very nice, and it's made out of the timber cedar. And I've got one other piece of wood here, and it's plywood, and it's got a coating on it. Now, this is wood, but it's manufactured. In the factory, they get layers of timber, and they lay them, the grain one way in one layer, and then the grain the other way, and then the grain this way, and they glue it and they compress it, and it gets very, very strong. Very, very strong. And I think plywood is a very good material for building with myself. And of course, the tables, okay, are made from bamboo. And if you're lucky enough to have one of our little table protectors, then that is made out of wood as well. So you could write that down actually. If you've got a table protector, that's made out of bamboo. And is there anything in our set that is made from wood? Yes, there is. And it is the little timber disc. Okay, the little timber disc. And that's actually made out of the cedar blind. We use our laser cutter and we cut them up. Okay, we use our laser cutter and we cut them up and we engrave it. And so it's recycled. Okay, it's recycled. And then we pop it in here and it's a nice little bit of branding. And so talking about that, that timber disc is the piece of wood that's in your set. But I want to show you one more material. One more material is ceramic. Now ceramic, it's a very, very important material, and it starts off like a clay, and it gets formed and then they heat it up to harden it. It's quite similar to glass. And there are actually quite a few scientific pieces of equipment that are made from ceramics, such as crucibles, evaporating dishes, pipe clay triangles, but that's sort of for more senior chemistry and not for the chemistry that we're doing in this course. So there we go. That's how we can classify the equipment according to the material it's made from. Now, what's another way to classify the material? Well, maybe not from what it's made, but maybe from whether it's rigid or flexible. So what's something that's quite rigid? Well, glass. Glass is very, very rigid. So rigid, in fact, that if I drop it, it won't bend at all. It will just break. And what's flexible? Well, foam. Foam is flexible. Look at this. This plane, look how flexible the wings are. It's quite light, but it's very, very flexible, and that means when I throw it and it lands, it's not going to break. So, woo! So we've got a flexible foam plane, we've got a rigid piece of glass, and what about some of the equipment in here? Well, anything that's made out of glass is rigid. Okay, anything that's made out of glass is rigid. So we can put the beakers, the conical flask, they're all rigid, and I think the magnet is quite rigid as well. Okay, the magnet is quite rigid. What's flexible? Well, certainly the see how you can squeeze the funnel. The funnel is flexible, so let's pop him here. The rubber stopper is definitely flexible. The vial is flexible, okay, and the pipette is quite flexible. Now this is a little bit tricky, isn't it? The thermometer itself, the plastic actually is a little bit flexible, and the lead is definitely flexible, so I'm going to put that there. The plastic spoon, okay, the plastic spoon is flexible, so we'll put it over here. What about the plastic plate? Don't flex it too hard because it might break, but it's hard to know. Sometimes when you're classifying things, it's actually quite difficult to decide which category they go into. You need to make a decision. I'm going to put it in the flexible, and let's have a little look. The timber disc, don't flex it too hard, particularly along the grain, because you'll snap it in two. Okay, so be very, very careful that you don't snap your... Notice with this though, it's not flexible in one orientation, but in the other orientation it is. So yeah, very interesting. I'm going to put it as a flexible one. The aluminium has got some flex, and the steel pan, a little bit sharp, so just be careful. It's quite rigid. I'm actually going to put the steel pan here, and this plastic lid here, that's definitely flexible, and in fact the base is flexible as well, and in fact the foam is flexible and the container is flexible. So we've got most of the objects are flexible and some of the objects are rigid. Now not everything is so straightforward. Let me show you something. Alright, so my leg bone. My leg bone is made out of bone, and the outer part of the bone is actually quite rigid. It's actually made from calcium salts, but the inside of the bone is very, very flexible. Now that's fantastic. That means, it's wonderfully designed so that those two different rigidity and flexibility together actually provide what we call a very strong object. Not a hard object. See, hard objects are brittle and they'll break, but this is a strong object. It's not going to shatter if you jump on it. It will sort of flex a little bit, but it will be strong enough, hopefully, not to break. So bone is a mixture of both rigidity and flexibility. How good is that? Same as, here we go. Alrighty, if you go bike riding. Okay, so I've got a very rigid outside part of the helmet and a very flexible inside of the helmet. So again, that provides some good protection, particularly if you're in a little bicycle accident. So fantastic. And of course, pool noodles. What are pool noodles? Would you say a pool noodle is rigid or flexible? If you said flexible, hopefully that means you've learnt something. So very, very good. Don't go around whacking people though. That's not very nice. So, all right, let me put this over here and move this across. Almost dropped on the floor, but that was plastic, so it would have been all right. And I'm going to get my bowl of water because we're going to try classifying according to whether things will float or sink. So, will it float? Will it sink? Well, this is a little bit, let's start with a really easy one. Let's start with the magnet. What do you think will happen if you put the magnet in? I think the magnet is going to sink. Whoop! It's more dense than water. That was easy. What about the stirring rod? The stirring rod's made out of glass, and I'm not going to drop it this time because I know it's quite brittle, but if I let go, yay! The stirring rod sinks. The stirring rod sinks. What about the wooden disc? What about the wooden disc? The wooden disc floats. If I push it under, pops straight back up. Look at that. It's less dense than the water. It's less dense than the water. What about aluminium? Now I know that aluminium it's a lightweight metal, but I do think it's denser than water. Yay! It floats in water, but we've got a little bit of a problem here, isn't it? It floats, but what about if I fill it up with water? Then it sinks. See, some things can be difficult to classify. Same thing for the steel pan. Hey, you might say it's less dense than the water. No, because if we fill it up with water, so it's actually more dense than water. Similarly, I probably can't even get this one to float, unless this is the beaker, of course. If I put a little bit of water in it, I can sort of make it float like this, can't I? Yeah, but if I fill it up with water, bye-bye! So a beaker is more dense, and so that would of course mean a conical flask is more dense. But again, he's flipped upside down. He's got some air trapped in him. But if I get rid of all the air, then he sinks. Let's put this beaker in as well. The rubber. This is a tricky one. What do you think? Like, it feels quite heavy, doesn't it? It feels quite dense. I think it's going to sink. What do you think? Let's put it in and find out. This is an experiment. Ready? It's more dense than water. It's more dense. Now the vial's made from plastic. Now if the lid is on, it's like a submarine, isn't it? It really floats really quite high above the surface. What about if I fill it up with water? What do you think? I get rid of all the air. So it's totally full. It's totally full of water now. Will it float or sink? Just floats. Just floats. Just floats. So the plastic is slightly less dense than the water. What about this plastic, the little plastic spoon? It's also slightly less dense. Slightly less dense. So the funnel, I'm going to make a guess. I think the funnel will float as well. Yes, the funnel will just float. But the plastic is very similar in density to the water. And I could actually make another submarine, couldn't I? Put a lid on there, on that plastic container. It really floats. Woo! pops straight up like a big boat. But if I fill it up with water, like this, whoa, one part, it's almost the same density as water, almost exactly the same density. Fantastic. The pipette's very tricky to do because it's actually very difficult to fill up with water totally. That can be a challenge to you. But I think plastic will be slightly less dense than water. And don't put your thermometer into the water because it's made of electronic parts, and so it won't work. You can put this part into the water and it will sink. And so the things that are made from plastic float. Plastic and wood float, but the things that are made from glass and metal and rubber sink. So if it's less dense than, or if it's more dense than water, it will sink. If it's less dense than water, then it will float. Well, that's it for this lesson. Hopefully you've enjoyed it, and I look forward to seeing you again in the next lesson. Bye for now. Hey everybody, in this lesson we're going to be using a dichotomous key to identify the different pieces of equipment in the Junior Chemistry Set 1. Now, a dichotomous key asks a series of questions, and for each question there's two possible responses, and you have to choose the best response in order to follow down to the next question. So let's give it a go, and I'm going to pull out this piece of equipment. Now I know what it is and you know what it is, but the question is, does the dichotomous key know what it is? Can the dichotomous key correctly identify it? Let's find out. So, is it from the Junior Chemistry Set 1 equipment? Yes, so we go down. Does the piece of equipment let any light through? Yeah, it does. It lets light through, so yes. Can it hold water? Yes, so we go down. Is it easy to see through? Is it transparent? Yes. Is it cone-shaped? Oh, no, it's not cone-shaped, so no. Does it have a lid? No lid. And so, is it a glass beaker? Yes, it's a glass beaker. Well done, dichotomous key. Let's try another piece of equipment. Let's try this. Okay, let's try this. It's on top of the conical flask. So, does the piece of equipment let any light through? No, it's opaque, so no. Is it made from metal? No, it's not made from metal. Is it, what's that say? Is it flat? No, it's not flat. A rubber stopper. Yes, that's a rubber stopper. Good job, dichotomous key. And me. What about the thing that the rubber stopper was in? Let's give it a go. Does the piece of equipment let any light through? Yes. Can it hold water? Yes. What's this? Is it easy to see through? Is it transparent? Yes. Is it cone-shaped? Well, it certainly has got part of it that's cone-shaped. Is the whole thing cone-shaped though? Well, this is a little bit tricky because I'm going to say yes. I'm going to say yes. And then it says it's a conical flask. Yes, that's true. So that was a little bit of a difficult question because I wasn't 100% sure of the answer, and you sort of have to go with the best answer if you're unsure. Okay, what about this red-blue thing with an N and an S on it? I wonder what it is. Does it let any light through? No, it's opaque. Is it made from metal? Well, I think it's made from metal. I mean, it's quite dense and it's hard. It's not wood, so I'm going to say yes. Is it magnetic? Well, I don't. How do I know? I have to test it on something. Okay, I'll test it on. Here we go. There's this. Oh, yeah, it is magnetic. It is magnetic. So, yes. Is it round? No, it's not round. Ah, it's a magnet. Yes! Good job. Oh, this is quite fun. I like this game. All right, this thing here. Does it let any light through? Yeah, I can see light through that. Can it hold water? Well, if I put water in it, it's going to pour out the end. So I'm going to say no. It's not a stirring rod. Oh, no! So where it said, can it hold water, I guess if you block the end, then it can hold water. See how sometimes dichotomous keys are not perfect? Or I'm not perfect. Can it hold water? Let's say yes. Is it easy to see through? No, it's not easy to see through. What's this say? Does it have a lid? No. Can you squeeze it? Well, you can squeeze anything, can't you? Like, I think that means does it flex when you squeeze it? So I'll say yes. Pipette? No, it's not a pipette. Oh, I'm going to go back to this. Can you squeeze it? Okay, well, it is quite rigid, so I'll say no. Can you put, what's this say? Can you scoop with it? I'll say no. And so it says it's a funnel. So for the funnel, this dichotomous key could probably be improved on. Okay, so I just made this one up myself. Okay, and I'm no genius, so I admit that it's not perfect and maybe you can do better. So if you're having a good old laugh at me, well, you can actually have a go at making your own dichotomous key, and then I can test yours and maybe I'll be laughing at you. No, that's not very nice. I wouldn't laugh at you. Maybe I would. What else do we have here? Okay. All right. This thing here. Does it let light through? A little bit, because it's translucent. Can it hold water? Well, you can in the end of it. You can hold water. Are you able to see through it? No, it's translucent. Does it have a lid? No. Can you squeeze it? Well, you can squeeze it, but it doesn't really move much. Can you scoop with it? Oh, I can scoop with this. Yes, it's a spoon. Yay! All right, so that was pretty successful. What about this one? Does the piece of equipment let light through? Yes. Can it hold water? Yes, it can. Can you see through it clearly? No. Does it have a lid? Yes, it's got a lid. It's a vial. Good job. Well done. So far we've only got one problem with the dichotomous key. Let's try this one. Does it let any light through? Yes. Can it hold water? No. Oh, it's a stirring rod. Well, that was easy, wasn't it? Well done. Good job. What about this one here? Okay. Does it let light through? A little bit. Can it hold water? Yes. Can you see through it? No. Does it have a lid? No. Can you squeeze it? Well, yes, I can definitely squeeze this one. Can you scoop with it? No. Oh no, it says it's a funnel. It says it's a funnel. Oh, that's because I went down the wrong path. Can you see I made a mistake? Where it said, can you squeeze it? I said yes, but I went down the no path. That was a bit silly. So can you squeeze it? Yes. It's a pipette. See, it's okay to make mistakes. It's good to sometimes think about your mistake and where you end up and say, oh, this is definitely not a funnel. Where have I gone wrong? Nothing wrong by asking, where have I gone wrong and what can I do to fix it up? Okay? So, there we go. It's a pipette. Let's open up this. And what do we got here? A little silver dish. Okay, little silver dish. Does it let light through? No. Is it made from metal? Yes. Is it magnetic? Well, I'm going to use my magnet to find out. Yes, it is magnetic. Is it, what's this say? Round. Yes. Ah, it's a steel pan. Well, let's try this one. Okay. Does it let light through? No. Is it made from metal? Yes. Is it magnetic? No, it's not magnetic. Ah, it's the aluminium dish. What about this one? Does it let any light through? No. Is it made from metal? No, it's made from wood. Is it flat? Yes. It is the, what's that say? The white plate? That's not a white plate. Oh dear, oh dear, oh dear. I think I know what the problem is. The problem is, I don't think that this wooden disc is actually on this dichotomous key. I've found a new species. Well, I never put it in the key. So there's another little bit of a problem. This dichotomous key doesn't have every single thing in the piece of equipment. But what about this? I've got a little plate. Does it let light through? Oh, I think I've just detected a problem, people. I'll tell you what the problem is, because it does actually let a little bit of light through. So, can it hold water? Yes. Is it easy to see through? No. Does it have a lid? No. Okay. Can you squeeze it? No. Can you scoop with it? No. It's a funnel. No, it's not a funnel. I know what the problem is. When I wrote this dichotomous key, it must have been in a little bit of a dark room, and I didn't notice that you actually, I thought it didn't let light through. Well, I thought it, that's right, I thought it didn't let light through. And so here, I wrote down no. And then, is it made from metal? No. Is it flat? Yes. Aha, it's the white plate. So again, a little bit of an issue with the dichotomous key. See, they're not easy to do, okay? And what about this? Does it let light through? Yes. Can it hold water? Yes. Is it easy to use? Oh, sorry, is it easy to see through? I'll say yes. Is it cone-shaped? No. Does it have a lid? Yes. Yes, it's the plastic container with the lid. Woohoo! And what about this one? Okay. Does it let light through? No. Is it made from metal? No, it's mainly plastic. Is it magnetic? No, I know that's not magnetic. Aluminium dish? That's not an aluminium dish. I know what the problem is. The thermometer is not on this dichotomous key either. You're probably thinking to yourself, you're probably laughing, aren't you? Jacob, have you got any of these right? Well, I've got most of them. I got most of them right. There's just a few that we've had a little bit of an issue with. And so I challenge you to do a better, more complete dichotomous key for all the equipment, and you can test it with your friends or your parents or your siblings and see how successful your dichotomous key is. Give them a piece of equipment that they just don't know what the name of it is. For example, the conical flask, and see if they can follow it down and get to the correct name for it. So there you go. It's a very, very powerful identification chart, but they are quite difficult to actually produce in the real world, I guess. So there we go. Hopefully you've enjoyed this lesson. And I look forward to seeing you in the next lesson. Bye for now. Hey y'all, in today's lesson we're going to be looking at some scientific equipment skills. Now for this lesson you are going to require a few extras apart from the Junior Chemistry Set 1, and a glass of water is very, very helpful, not to drink, but to actually use as a water supply. I'll have a bowl down here that I'll use as my waste, so I can tip my waste and do my washing up in this bowl. And I'm actually going to be using some food colouring this lesson, and I think this Queen's food colouring is very, very good. Good sized bottles, easy to use, nice to squeeze. So I think that's a great food colouring to use personally, so I'll be using this one. Also, you'll need some sugar. So I've got some sugar in this bowl, some salt. Now the salt can come in different containers, whatever. Pepper can come in different containers. You might have like just a container of crushed pepper, but not peppercorns. You need actually to have like crushed up pepper. Some citric acid, and some flour. Okay, so a few extras for this lesson. Let me pop these down here. And don't forget to try and keep your workspace nice and clear. That's very important, clear and clean. And so I'm actually going to add just a little bit of food colour to this water so that you can see the water quite clearly. It's up to you whether you do that or not, but I'm going to do it. There we go. Oh, bit of a squirt there, probably a little bit too much. Anyway, that's done. I might, oh, look at that. I can see the food colour dispersing, or diffusing, I should say, and I can actually give it a bit of a mix. Oh, that's really quite dark. Oh, perfect. Doesn't matter. Okay, so what's the first skill? Let me have a little look here at our worksheet. Using the pipette. Transfer pipette or transfer water from the beaker into the conical flask by squeezing the bulb of the pipette. So we'll need the beaker and the conical flask and the pipette. Now the question is, how do we get water into this beaker to start with? Because this might not pour very well. Let's have a little look. Woo! Oh, it didn't pour that fantastic. Oh, that's very, very full. And I've got a little bit of a mess there, but that's okay. I've got some water in my beaker. I wonder if you can do a better job than what I've done. I'm sure you can. And so I need to transfer water from there into here. So I'm going to squeeze the bulb of the pipette, put it in the liquid, and then release. Oh, and water goes up. So now I can squeeze and transfer the water to the conical flask. Squeeze, release. Squeeze, release. Squeeze. Oh, I blew some bubbles. Release. Squeeze. I could keep it squeezing. I could keep it squeezed and bring it over here and then release like so. Squeeze. Look at this. When I squeeze, notice that I can blow air bubbles. That's important. See, when you're squeezing, you're actually squeezing something out of the pipette. You see, this pipette is not empty. It might look like it's empty, but it's actually full. It's actually full of air. And that's why when we put the pipette into the beaker, water doesn't go into the pipette because it's already full. There's air molecules in here and they're buzzing around and they're pushing against the wall and they're pushing actually against outside. And so I actually have to get rid of some of them. And then when I release it, air pressure actually causes the water to get pushed up. Believe it or not, the pipette does not suck up the water. The pipette does not suck up the water. Water is actually pushed up by air pressure. How's air pressure pushing on that liquid? Well, it's actually colliding and pushing down on the liquid. And so now, by squeezing and releasing, I'm allowing the water to get pushed up. So that's how we transfer the liquids. Now, here's a challenge. Can you 100% fill this pipette with water? So can you 100%, are you able to fill up this pipette 100% with water? Like, I wonder what percentage I can fill it up with. Let's have a little look. If I squeeze it really tight there and then I release it and sort of help it. See, it's not 100% filled up with water, is it? That's probably only about maybe 60%. So what about if I squeeze it again? Well, the problem is I just squeeze out the water and then the water goes back in. Do it again, squeeze out the water. That's not 100% filling up the pipette. How do I get rid of this air? Do you have any ideas? I think I've actually got to turn it upside down. I'm going to give this a little bit of a flick. Ah, hey, oh no. And I don't want to put my mouth on it and blow it or anything like that. Is any going down? What about if I give it a bit of a squeeze here? Will. Okay, all right. What about if I squeeze out some of that? Ah, there we go. I've got water there where my thumb and finger are pinching. And then I'm going to, hello. Come on. How do I? It's not easy, is it? How do I do it? How do I fill up the pipette with water? That's a challenge, isn't it? I'm not even sure. And I'm supposed to be the science teacher. It's like a little airlock there. There's air here and it's stopping the water from coming down. I bet some of you are screaming at me, do this, Jacob, you can do it. Oh, hang on. While I was doing that, something happened. Let me do it again. Jacob, do this. Yes. Yeah, help me. I don't know how, but clearly what you have to say is this. You have to say, Jacob, help me. Oh no, Jacob, do this, and then it happens. Oh, that is, I learn things new every day. I don't know what actually happened there. It must have been the way that I was shaking it. So I am about to do that, and ta-da! Dun, 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 dun. All right, I have done it without making too much mess. So now don't squeeze it out yet, okay? Don't squeeze it out yet because we're going to need this for the next little activity. And the next activity is looking at what we call volume. And volume is how much space something takes up. And so the question is estimate and then find the volume of some of the equipment. So estimate and find the volume of some of the equipment. So the first one is the pipette. The pipette. Now the question is, how much water in mils is in this pipette? So now I know that this is a 2 ml pipette, but having said that, the 2 ml is, the mark is about here, so that's about 2 ml. Then I have to think to myself, well, it's about 3 plus 4. I'm going to guess 4 mil. That's my guess. Now, you can do your own guess. So an estimate is basically a guess, and I'm just going to write the number 4. Okay, so I'm going to write the number 4 next to my estimated volume. What is the actual volume? Well, to find that out, I'm going to pour that liquid back in there. And I've got a measuring cylinder that's got some numbers, 2, 4, 6, 8, 10. And the measuring cylinder is fairly accurate. It's not really accurate, but it's accurate enough for this. So I'm going to now squeeze all the liquid out. Squeezing all the liquid out. Out you go. Blub, 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 blub. And I have to get my head down here, and I have to try and read those numbers. 2, 4. That's 5. That's 5 mil. That's 5 mil. So my estimate was close. The actual volume was 5 mil. So that's not too bad. I'm actually fairly happy with that estimate of mine. Okay, so what about, says the vial. So I've got the vial here, and I'm just going to take off the lid. So how much water will go into the vial? What's the estimate for the water going into the vial? Now, how do you even guess this? Now, 1 mil is 1 centimetre cubed. Okay, so if you had a little centimetre by a centimetre by a centimetre, that's a cube. So I'm thinking, could it be like 1, 2, 3 centimetres tall? And then I'm like comparing it to the height of the beaker. So this beaker, the 10 goes to there, There's an 8, 10, 12. I think that this beaker is like 13 milliliters total. They're about the same height, and that's about a third. So a third of 13 is, what's that? About 4 mil, something like that. So I'm going to guess that it's actually got a estimated volume of 4. Okay, an estimated volume of 4 mil. See that? Now, what are you guessing? You might have a different way to estimate, but this is going to be my way. And how will I work this out? Well, I might actually bring the liquid up to the 10 mil mark. That's what I'm going to do on the measuring cylinder. So I'm not measuring cylinder, on the beaker. So I'm trying to get it at the same height as my eyes. Okay, let me double check. Okay, now let me tell you that later on in high school you are going to learn how to measure volumes a little bit more accurately. Okay, but for now this is okay. But if you're a science teacher, please don't scream at me saying, that's not how you do it accurately, Jacob. Well, just for now, it's okay. So there's 10 mil in here, and I'm going to now transfer liquid to the vial. Can you see how I'm going to work out? I'm going to use deduction. Not like mental deduction, but actually like arithmetic deduction. There we go. So that's now full. And now I come here and I look at the new value and it's at 4. So I've gone from 10 down to 4. So 10 minus what equals 4? 10 minus 6. 6 mil. I was out by 2 mil. That's actually quite a lot. Okay, that's actually quite a lot. Did you do better? Did you do better? Hope so. All right, so the next one we're going to do is the large plastic container. So, whoa. Let's empty it first. Okay, the large plastic container. Look at that. That looks quite, well, it's very low. It's very low, but it's very wide. Oh. Oh, this is difficult. There's 10 mil in here. This is higher. What are you thinking? What are you going to write down for the volume for your plastic? Whoa! I'm back. What are you going to write down for the volume for your plastic container? I don't want to show you my estimate until you write down your estimate, okay? Because I don't want you to copy me, basically. Can I copy yours? I wish I could. Okay, that's it. That's my estimate. What do you think? I've written down 20. I've written down 20 mil. Okay, let's find out. Here's 10 mil. Whoop! Oh! Okay. Now let's get another 10 mil into this beaker. So it at least holds 10 mil. And okay. So I've got 10 mil in this beaker now, so I'm going to transfer the liquid. Oh, I'm not so ridiculously hit. I might actually be very, very close, you know. Now I don't want it bulging. I don't want it to bulge. That's not fair. I just want it flat. So I'll say that that's full. And I've got 3 mil left in there, so 10 down to 3, 7. And so 7 plus the original 10 is 17 milliliters. How did you go? I guessed 20 and found it was 17. So I overestimated. How did you go? Did you get it exactly right, or did you over or underestimate? And now I've saved the most difficult to last. The most difficult to last. And that is, oh no, the volume of the funnel. Oh, but it's not straight, Jacob. Oh, why? This is torture. Okay, so I know something that you probably don't know yet, and that is that the volume of a cone is, I think it's 1/3. I think it's 1/3 of if it was like a cylinder. So I think that's right. I could be wrong. You might have some parents or teachers, Jacob, teaching our kids the wrong thing, but I think that's about right. Well, hang on. Hello. I've got a bit of a... No, that cone's not the same as this cone. No, that was... So I'm looking at this going, okay, if that's about 10 mil, and I said it's about 1/3, I'm going to guess 3.5 mil. That's it. I'm actually going to go 3.5 millilitres. That's my guess. 3.5 millilitres. Now notice I don't actually write mils down, because I've actually got it written in the title there. So I don't have to write down the mils. Alright, so I've said 3.5. Let's do it by deduction again. Shoop. This is actually very interesting, isn't it? Very interesting. Some of you are probably like, no, not really. Okay. I'm going to have to block the funnel, otherwise it will hold thousands of litres. If you don't block the funnel, it will hold, because you can keep pouring it in. Okay, in we go. Now, oh yeah, the water has gone down, and I've filled it up. So there we go. It's full, and that value there is 5. That value there is 5. So how did I go? I guessed 3.5. My estimate was 3.5, and the actual volume was 5. Okay, so I was under by 1.5 mil. Am I any good at estimating? Well, we could actually play a little bit of a game, do you know? We could actually play a game to see what your score was. So I'm actually going to add up. So I'm under, but I'm over, and then I'm under. I was thinking about adding up all the, probably, you know, to actually work out how good you are at this, you actually probably should work out what your difference is. So the difference in this case, this one has a difference of 1, this one has a difference of 2, this one has a difference of 3, and this one has a difference of 1.5. And so if you actually add up all the differences, 3 plus 3, 6, 7. So my total difference was 7.5 mil. So you could say that my score is 7.5. Now, if I had a score of 0, that would be perfect. That would mean that each estimate was the same as the actual. Why don't you work out what the difference in mil is for each one of yours and add up your differences? And if your differences is less than my number of 7.5, that means you beat me, okay? And if you ever see me, you can come up to me and say, Jacob, I'm better at estimating volumes than you are. And I will say, congratulations, good job, well done. So there you go. Pin a prize on yourself if you've got less than 7.5. Fantastic. Okay, so... quite enjoying this, to be honest. I quite like I'll let you on a little bit of a secret here. We just did some mathematics. I know. Here I am telling you it's a chemistry course and I'm sneaking in mathematics. But you know, maths Maths is actually a very, very good subject. Scientists use maths all the time. Some people say it's the most pure of the sciences. Now look at this. I don't have a wiper upper, so I'm just going to use my hands. Perfect. There we go. That's my wiper upper. No, I can do that this time. And I'll just make my hair nice. Oh, my hair's a bit blue. Because the only chemical was water and food colouring, and that's not going to be poisonous. So, next one, pouring. The next skill is pouring. Is it pouring at your place? Is it raining? By pouring the liquid onto the stirring rod, the flow of the liquid can be controlled. And so there's a picture of someone pouring water from a conical flask onto a stirring rod and into a beaker. So I'm going to give that a go. Now, I'm the one who actually wrote the worksheets, and so let's see how successful this is. Here's my stirring rod, here's my beaker. I'm going to put the stirring rod into the beaker, and I want to transfer the water into the beaker without spilling it. So I'm saying that if you put, does that work? Look! 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 This is wonderful! The stirring rod channels the water, don't tap it too hard, down to the beaker. That was very successful. I wonder if I can do it the other way. Oh, try that way. Will that work? I don't know. Oh, hello. Wow. Now this is because of what we call cohesion forces. There's actually a cohesion and attractive force between the glass and the water called a cohesion force. Look at that. It runs down the stirring rod. I could think of some practical applications. Why do you need gutters? Why do you need downpipes when you could just have some people actually just have a chain and the water follows the chain down. Whoop, I just dropped some because there was some left there. So there we go. There's a skill for transferring liquids. You can pour it down a stirring rod. Yay! I love it. Love it. Okay. So the next one is, the next skill is stirring and not banging. Now I've got some equipment here, and so I should probably put that away. So I'm just tap off the water off the funnel. Tap the water out of the vial. Now this would be best. It would be best just to rinse with some fresh water. Let it dry, drip dry, and then you can put it away. Now if you're putting it away for a long time, you should probably dry the equipment, but it can actually go away wet because this foam is very robust and it's got a good lifespan, and you can actually pull it out and wash it. So good stuff. All right, stirring. All right, so we're going to have a little bit of a practice at stirring, and we have to stir this water fast enough so that we get what we call a vortex. So I want you to hold the beaker in one hand. Now if you're left-handed, you probably got to hold it in your other hand. But I'm right-handed, so I'm going to hold it in my left hand. And I'm going to stir. Now don't bang. If you go bang, bang, bang like that, you will punch a hole through the beaker. And that's not good. You'll have to get a new one. So I'm going fast enough. That I get like this swirl, this vortex, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm sort of stirring about as fast as I can possibly count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Maybe you can count faster than me. Okay, I'm not too sure. And so the question is, now, will it dissolve? Will it dissolve? That's a good question. We've got some different substances, and we're going to see whether they dissolve or not. Okay, whether they dissolve or not. Now, it will actually be better if I use just some plain water. So I'm going to get some plain water. I'll be back in a moment. I'm back. All right, so will it dissolve? So I think we should put about, half fill the beaker with water. Okay, so I'm going to half fill the beaker with water. So now the measurement goes up to 10 ml, but the beaker actually probably holds about 13 or 14 ml. So when I say half fill, I sort of mean like visually half full. See that? So it's about half. Oh, that's a little bit too much. It doesn't have to be exactly the same. All right, so the question is, does sugar dissolve? That's the first one. And so I'm going to get my spoon, and I'm using just some white crystalline sugar. Some white crystalline sugar, not caster sugar, not brown sugar. And I'm just getting a spoonful, a little bit more than a level spoon. Now, don't get the spoon wet. Don't get the spoon wet. I'm going to put the spoon in, and the first thing that I can observe is that the sugar sinks to the bottom. The sugar sinks to the bottom. And I can see sort of little crystals, but I can also see a little bit of a haze. I can see a little bit of a haze forming there. And if I stir it, remember I showed you how to stir? Hold with one hand and spin really quickly with the stirring rod until you get a bit of a vortex. And I can see the sugar going around and around and around like this as part of the vortex. Now occasionally I can bring my stirring rod to the middle, but I'm going to go around and around and around and around. Oh, it's disappearing. The sugar is disappearing. It's going into the water, and that word is dissolving. That word is dissolving. The sugar is dissolving. It's a better word than disappearing. Because disappearing sort of sounds a bit like magic, and that just totally is gone. But it's not actually totally gone. It's the particles are broken up, that they're so small that you can't see them. Okay, so that's what's happening. The particles of sugar are breaking away from each other. Okay, so the particles of sugar are actually breaking away from each other, and so now you've just got individual sugar molecules spread throughout the water, and because they're so small, you can't see them. So, observations, where you can put things like the sugar sinks, the crystals get smaller, the sugar dissolves. Is it soluble or insoluble? Well, soluble means it dissolves, and insoluble says it doesn't dissolve, so it's definitely soluble. Soluble. There we go. It's soluble. Okay, what about salt? Okay, well, to make this a fair experiment, we need to tip out the sugary water. So to make this a fair experiment, we have to start with the same conditions. And remember, with the same conditions was half full of water, okay, or close to. These pipettes are really good, aren't they? Whoop. That's half full of water. And some sugar. Oh no, my sugar's in here. Sugar, salt. Sorry, salt. So what am I going to do? I'm going to grind some salt into some paper like this. And if I get my little spoon, and if I put a little tiny fold in the end of the paper here, actually, I could use my funnel. Yeah, use my funnel. Although it could be a bit wet still. I'm going to put my funnel like this, and then I'm going to tip the salt into the funnel and then into the spoon. Because I want about a... Are you going to go down? Yeah. Whoop! Woo! I got a lot more than a spoonful. Wow. That's quite good. That's perfect. That's perfect. There we go. I've got my spoon of salt. Tip that in. And let's see where the salt dissolves. Again, the salt sinks. Oh, it's a lot more, I guess, hazy or milky. Right? Isn't it? Yeah, a lot hazier, a lot milkier. It seems that the crystal size of the salt is smaller than the... Oh, it's already dissolved. Now, I'll let you in on a little secret. Chemically, salt dissolves very differently than sugar. Sugar, the molecules break apart from each other, but the molecule of sugar stays whole. Whereas sodium chloride is not a molecule. It's actually two repeating units, sodium chlorine, sodium chlorine, sodium, or I should say sodium chloride, sodium chloride. And when you dissolve it, the sodium breaks up from the chloride. So it goes sodium and then chloride, sodium chloride. So in actual fact, the compound is breaking up. Now that's sort of high school stuff, but you know what? It doesn't matter if you learn the truth from a young age. Salt is very, very soluble. Absolutely. Tip him out. Soluble. Soluble. Pepper. What do you think? Pepper. Some people say that my hair is the colour of salt and pepper. My wife is actually saying it's more and more salt all the time, i.e. it's not white and grey, it's just white. That's what happens when you get older, I guess. But, hey, at least I've still got hair. So now, let's get some pepper. Here we go. Oh, it's like a cooking show, isn't it? Hey, put it on the food, on this steak. That's perfect. And I need some water. Might just dunk it in this time. There we go. That was a fast way of doing it. And about a spoonful. Okay. Come and get into my spoon of pepper. Perfect. Now, once I did a very nasty thing. I didn't know it was nasty. I thought it was just funny. And I actually blew some pepper into my friend's eyes. It was a disaster, actually. I really wish I hadn't done it. I did it as a bit of a prank. And he really got irritated eyes, and it wasn't good at all. Sometimes pranks are just not good. Okay, so yeah, be careful when you do a prank, because sometimes pranks are not funny. If a prank involves anybody getting hurt or mocked or laughed at, then it's not a very good prank. Okay, so think about that if you ever do a prank. Now I'm seeing that the color changes color. The pepper does sort of started out floating, and now it's sort of sunk. I've got some pepper. Yeah, I've got some pepper reaction happening there. Oh, what about you? Okay. Oh no, not again. Oh, bless me. Okay, all right, having some reaction to the pepper. Oh, does it dissolve? I think partly soluble. Okay, partly soluble. I have to do a bit more investigation. I have to do some wash up actually here to work out exactly how much it's dissolved, but I'm going to say partly soluble. So I guess I might actually say insoluble, you know. I might say insoluble. Look, by putting the word in front of the word soluble, it means not soluble, insoluble. Citric acid. Okay, I'm going to scoop up 10 ml of water, or half a beaker of water. Now I'm using this citric acid from the shop, and again I need to get a spoonful, and so I'll do it like this. Tip in my citric acid, and you know what? Citric acid is one of my new best friends. I am not joking. I taught science at schools in high schools for like 25 years. Barely touched citric acid. We used a lot of hydrochloric acid, but I've actually found that citric acid is a great alternative with many experiments, and I'm a huge fan of it because it's so safe. One of the reasons it's quite safe. In goes the citric acid, and stirring, it's sunk to the bottom. The crystals are getting smaller, they're swirling around, they're slowly disappearing, and they're gone. Very soluble, extremely soluble. So citric acid, soluble. And the observations, you can write down your observations. Soluble. Ta-da! soluble. And last but not least is flour. Flour. So I've just got some, it's self-raising flour. Oh, hear about the little flour kits? They're all by themselves, and someone said, do you guys need help? And they said, no, we're self-raising flour. Okay, it wasn't funny. Maybe your mum or dad or teacher got that joke. Still not very funny, is it? Okay, anyway, self-raising flour. It's got a little bit of, I think, bicarb soda in it. And in you go. Oh, floats on the top. Oh, and then it starts sort of raining. Starts raining. Oh, yay, 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 yay. It's gone very milky. I don't think flour is particularly soluble. I'm thinking, look at that. Now, remember how I said don't do pranks because they're not funny, but if your mum or dad asks for a glass of milk, no, that's not funny. Okay, don't do the prank. All right. Look at that. I would actually need to look at this under a microscope to determine whether it's dissolved or not. If I could see the particles under the microscope, and I know some of you are saying, Jacob, look under the microscope. Well, maybe I'll see if I can get the microscope and have a look. I should do that, shouldn't I? Okay. All right. So for now, I'm going to say not soluble, insoluble. All right. I wonder if I can set up a microscope. Oh, let me see. Let me see if I can do it. Oh, the things I do for you. So I've got my microscope and I can look into it, but you can't see through my eyepiece, so I'm going to pull out the eyepiece and I'm going to put in the little camera. So I've got a camera and you'll be able to see that feed in a moment, hopefully. So let's hopefully I'll put that there like that. And I've got a glass slide. I've got a glass slide. And I might actually just tear a little tiny bit of a logo. So I've got my logo, the Tiny Science Lab logo. And let's put that onto the glass slide. I'll just dry it first. And you know what? I might actually just put a drop of water on that. So let me put a drop of water onto the paper there, just so that it's wet. That might actually help us see the image a little bit better. I'm not too sure yet. Let's find out. And I've got a glass cover slip that I'm going to put on top. And let's pop him under. And let's see what happens, shall we? So under we go. And we'll need some type of focus. Let's see, maybe it's too dark. Maybe it's too dark. I'll try and really brighten the light through the paper. Let's come down a little bit. Hang on. Whoa. Oh. This is actually... Whoa. This is awesome. Do you know what you're actually looking at here? You're actually looking at... Let me show you. See the green conical flask on that logo? See the green conical flask on that logo? This is what you're looking at. You're actually looking at the green of the conical flask. That, my friends, is the green on the conical flask. I'm not joking. That's incredible. You can see the fibers of the paper. See that? You can see the fibers of the paper. And here is the blue text. That is the blue text. And there's some air bubbles there. So the blue text is actually made up of multiple colours. Look at that. The yellow, the magenta, the cyan. Oh, I love it. This is so interesting. So, oh, there's a hair in the paper. Yeah. And then back over to the green, where's the green logo? There's the conical flask there, there's the little bit of green. So the big question is the milk dissolved or not? Is the flour dissolved or not? So I will need to get a drop of the, I'll give it a little bit of a stir. So it actually settled while I was doing all this. I could actually see that the flour had settled, which is a big sign to say that the flour is not dissolved. So I'll put a drop of the flour water, and then I will put a glass slide on top, and then we'll bring it into the, oh, there we go. Look at that. The flour is insoluble. That's all those little tiny pieces there. Okay? All those little tiny chunks. That is undissolved flour. Different sizes. Okay, different sizes. But how interesting is that? The flour is insoluble. Now that, my friends, has to be one of the most enjoyable science lessons I've ever had. I'm not too sure why. I'm a very simple person, measuring volumes, investigating solubility. Now you know why I like science. Very interesting, and to have the time to investigate it, love it. Anyway, I hope that you enjoyed this lesson as much as I enjoyed this lesson. Too bad if you didn't, because I got a lot out of it. So anyway, it is what it is. But I loved the lesson. Okay, anyway, I look forward to seeing you next time. Bye for now. Hey everyone, in this lesson we're going to be exploring temperature. Now you didn't think I was going to be staying downstairs the entire time in the studio. Now I know my voice is a bit tinny, and the reason is we've got a steel ceiling, and so that reflects the sound, and we've got some fairly hard floors that also reflects the sound as well. So it's not the ideal filming conditions for the audio, but I'm sure we'll be able to cope today. Now for this lesson, of course, you're going to need your junior chemistry set, and you'll need the thermometer. Now when you get the thermometer out, don't grab the probe. Okay, don't grab the probe, because if you grab the probe with your finger, the silver part, then that will change the temperature. So just hold the thermometer by the case and by the lead. Now you'll also need today a broom, because afterwards you're going to sweep up the house. No, you're going to need the broom to stay safe, and I'll show you why in a moment. And you'll need some sticky tape. So let's just measure the temperature of the room. So if I sort of wave the probe around a little bit, at the moment it reads 25.0 degrees. And oops, going down a little bit, 24.9. That probably means it was a little bit warmer in the case than the room, which is not all that surprising, because if the case is closed, that can actually trap some heat, can't it? So when you bring it out of the case, it might be a little bit cooler out of the case. And indeed, we're at 24.7, and I think, or 24.6. You know, the question is, how long do you wait for something to stabilize? I might call it 24.6 right this moment. Okay, so 24.6 degrees is about the temperature of the living area of the room. But what about the temperature of the floor, or the middle of the room, or even up near the ceiling, the top of the ceiling? Is it the same temperature throughout the whole house? Well, I don't think so, because I remember one time I was changing a light globe and I was up on a ladder and it was really hot. So let's find out. Let's do a little bit of an experiment. So I'll take my broom and I'm going to get a little bit of sticky tape and just stick the lead to the broom like that, so that we've got the probe poking there. And then the first thing I'm going to do is, well, we're at 24.1, but that's okay because we're going down to the floor. So down to the floor, and I'm going to put that probe sitting at the floor, and we'll see how the temperature changes at the floor. There we go. Now, good question to ask is, how long do we leave it there? Okay, how long do we leave it there? It's good being on the broom because I don't have to bend over and put it on, although I guess it will just like sit on the floor due to gravity, wouldn't it? So we're at 23.9 and it's not really changing. So, I think we'll call that 23.9 degrees. The temperature of our floor in the lounge room is 23.9 degrees. So let me write that down on the table, 23.9. I wonder what the temperature of your floor is. Hopefully you're measuring it right now as well. All right, now let's go to the middle of the room. So here we go. I'm going to get the broom and I'm going to hold it about the middle height in the room, okay? Now, will the temperature go up, stay the same, or go down? My hypothesis is that it's going to go up, okay? That's my hypothesis. And we're at 23.8, so that actually looks like it's gone down a little bit. I don't believe it. Science. Sometimes it drives you crazy, doesn't it? 23.8, but we have to be honest. Okay, we have to be honest. I'd like it to be, you know, higher, but it just isn't any higher. It's 23.8. That's just what it is. What can I do? It's not changing. All right, I'm surprised, but I'm going to write it down. It seems that the middle of the room is slightly cooler than the floor. I don't understand that at all, but there we go. I'm going to write it down, 23.8 degrees Celsius. I wonder what about you? Are you getting a similar result to mine, or is yours a little bit warmer? Okay, now I am sure though that when I bring this probe up to the top, to the ceiling, it's going to go up. I'm sure. It's at 23.9 now. Well, I've written down 23.8, so I'll leave it there. Okay, let's go up. Up we go. I'm going to go all the way into the corner, as high as we can go. Oh, here we go. Up, up. I'm stretching. We've got high ceilings here. I think they're 12-foot ceilings or something. Ooh, 3.6 meters, but there better be a difference up there, that's for sure. What do we got? 24.1. Okay. Oh, that's a relief. With all that effort, I wouldn't have been very happy. I wouldn't have been very happy at all if the temperature didn't go up. Okay. All right, let's do one more. And we're going to call it 24.1. Okay, now that we've got those results, let's go down to the studio and we'll do a graph. Okay, so let's go. Okay, so back down in the studio and let's graph these temperatures in the different levels of the room. So whenever we have a graph, we have to have a title, and the title will go up the top. And so it has to say something about what you've just done. So we'll say it's the temperature in lounge room. There we go. Possibly I should have put temperatures because it's plural, but that's okay. And then down the bottom, that's the thing that we're sort of changing. And so we've changed like the location. Okay, so we changed the location. So I'm going to put the word location. And we had the floor. And we had the middle of the room, the middle. And we had the ceiling. Okay. And then on the y-axis, or the vertical axis, we're going to put what we measured. And so we measured the temperature. I'm writing it down in vertical here. And I personally love starting graphs at 0. That's my favourite. And I have a look at what we went up to. We went up to went up to 24 degrees. So I want to try and use up most of the graph. So if I go 5, 8, 10, 15, 20, 25, 30. So I'm going to go up by 5s. Okay, so 5 and 10, 15, 20, 25, 30, 35, and 40. And so the floor was 23.9. So the floor was 23.9. So there's the 20. There's the 25. So 23.9 is about here. So I draw a line across here. Now I probably should use a ruler there, but there we go. I didn't. And I might even hash this. So this is actually a column graph. Now, in science, we have to choose the correct, in maths, anything you do, you have to choose the correct graph to use. Now, we can't do like a normal line graph because there's no relationship numerical. There's no numerical relationship between the floor, the middle, and the ceiling. Unless, of course, we said the floor was a 0 height, 0, and we went up like in centimetres or something like that. Then we could do a line graph. But because we just went floor, middle, ceiling, we can't really do anything else. All right, now I have found a ruler here. I have found a ruler, and I should actually rule around this column. Okay, I should rule around this column so that it's nice and clear. See, the idea of graphs is that they are to visualize. They are to help visualize the results, and that's a good start. Now, strangely, the middle of the room, 23.8, was a little bit cooler. So I have to actually come a little bit lower. That was quite a little bit strange. And you know what? I'm going to do the hashes slightly different this time. Slightly different angle. Okay. And they're going the other way. Zoop. And the middle room slightly lower. But then the ceiling was 24.1, and so it was higher than the others. So I'm going to put a line across there like that. There we go. And what sort of hash do you want me to do? I don't know. I might go zoo like this. What do you think? There we go. You can really see the difference between the two. Of the three things. And I should put a nice border on it as well. So, now the temperatures were actually a lot closer than I thought they would be. And so there's not a huge difference. The one surprising difference that I had, of course, was that the middle layer was actually slightly cooler than the floor, when I expected it to be a bit warmer because typically hot air rises. Now, why does hot air rise? That's quite complicated, and I've been thinking about it a lot today, and I don't really have an answer. I think I might actually have to Google it. I mean, the higher the temperature of air, the faster the air molecules are moving, and the further they are apart, and so they're less dense, I guess. But then even the question is, why does the less dense air rise? It's a good question to ask. There's our column graph. How about we now go do an experiment, and not an experiment, but let's go explore and find out the temperature of the cold water from the tap and the hot water from the tap. So let's go. Okay. Okay, so what's the temperature of the cold water from your taps and the temperature of the hot water from your tap? Let's find out. I'm going to do it with my tap in the bathroom. So first up, I'm going to turn the cold tap on. I think this is the cold tap. I hope it is. And I'll put the probe under the cold tap, under the cold water, and let's see what temperature it goes to. Okay, we're at 22.7. Now I don't want to run this for too long because it's wasting water. Probably would have been a better idea just to put the water into a glass, and that way I wouldn't be wasting the water, but it's for science and it won't take long. So we're at 21.1, and I think that's stabilised. So my cold tap water is 21.1 degrees Celsius. Let's write that down. I wonder what your cold tap water is. Now let's find out what the hot water tap is. Now I have to let it run for a little bit because the hot water system is about 20 metres that way, and the pipes are full of cold water, and so it will take time for that hot water to get here. Okay, it won't take that long. I can feel it getting warm now, and so we'll be able to see the temperature going up. Now our water is heated by the sun. It's solar hot water, and it's been a fairly sunny day today, and so I'm expecting the temperature to be pretty reasonable. Not crazy hot, but pretty reasonable. And at the moment we're at 41.1, 41.6, 42. I don't actually think it's going to get too much. I think it might even like peak out at about 45 degrees Celsius or something like that. Yeah, it's not that hot. 43.1, 43.3. I mean, that's about the temperature of what I would call a, nice, not a hot, but a hot shower. I'd be happy with that temperature. So here we go. Here's the final reading. I'm going to call it 44.7. That's what I'm going to call it. Oh, it's just gone up to 44.9. 45.0, 45 degrees Celsius. That's it. I'm going to call it that. Okay, let's go downstairs and we'll do a little column graph with those findings. Okay, let's go. Okay. Well, I've got very clean hands now because of all that running water. And so I'd like to graph these results so that we can see visually the difference in the hot and the cold tap. So remember what we start with? The title. And in this case, the title is going to be the temperature of tap water. So the temperature of tap water, and down here we will put the type of tap. So I'll put tap, and we can start with the cold. Okay, now it is a little bit difficult me writing sort of sideways here, so excuse me if I'm like not writing the nicest. And the hot, which I probably should have had red. And then down here on the vertical, let's go temperature, and we need to have our units, degrees Celsius. And again, I'd like to start at 0, and we can go up by 5s again. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. And the temperature of the cold water was 21 degrees. So I'll go 5, 10, 15, 20, and 21 is about here. There we go. And how about I use a ruler? Teachers are shouting out, use a ruler, Mr. Strickling, use a ruler. Okay, I'm using a ruler. And there's my ruler. And I'll do a bit of a dash like so. And the hot water was 45 degrees. Whoa! Up. Up. And there, what a big difference that was. And so what a graph does is allows us to see the differences very, very clearly. There's a significant difference between the temperature of the hot water and the cold water, isn't there? Massive difference. So there we go. Beautiful graph, column graph. And again, it has to be a column graph because we're calling them cold and hot. There's no numerical relationship between cold and hot. So column graph is perfect for that. Okay, let me pop this down. We haven't quite finished the lesson because we're going to just look at the temperature of our hands, and we're going to explore something called friction a little bit. And so if you hold the probe this time in your hand, you will see the temperature going up, and it will be really good to record the temperature of your hand. So it takes a little bit of time to stabilize. 31.2, 31.6. I wonder who's got the hottest hands. Me, you, your friend, your sister, your brother, your mum, dad, your uncle, your grandmother. I don't know. Who else? Uncle and auntie. Who's got the hottest hand? 32.5, 32.6. Okay, 32.7. I think it's pretty stable now. So I might write down, 32.9. All right, I'll just get my pen and write that down. 32.9. Perfect. Oh, it's gone up to 33.1. Pain. 33.2. Okay, I'm going to call it that. But now it says, if you rub your hands together, what's the highest temperature you can get them to? So at the moment, now I've got 33.3. Well, that is a nice round number, isn't it? Okay, so everyone, clap your hands together and start rubbing. We're pushing your hands together that the surfaces are pushing over each other. I can actually feel it getting quite warm. Whoa, that's actually getting hot. Oh, you can feel the heat. Feels delicious, doesn't it? Okay, and push and rub. It's getting hotter. I'm sure it's getting hotter. Okay, here we go. Let's see. Oh. Now don't rub the probe though. Don't rub the probe because that's not good for the probe. But mine's up to 34.3, 35, 35.8. If you had two people next to each other, you could like share the probe backwards and forwards. 36.2, 36.6. Look at that. I wonder if I can get to 37. 36.5, 36.8. 37.1. Oh, and it's going down now, so I might just call it 37.1. Were we able to get a higher temperature than that? Hope so. Anyway, that's it for this lesson, and I look forward to seeing you in the next lesson. Bye for now. Hey everyone, in this lesson we're going to further explore temperature. So I've got the fridge and below it is the freezer section. And the question is, what do you think the temperature inside the fridge is? What do you think the temperature inside the freezer is? So there's an opportunity to have a guess or an estimate. I guess you could even call it a prediction. What are you going to write for the temperature of the fridge? What are you going to write for the temperature of the freezer? Jot it down, and then we can find out using our temperature probe. All right, did you write down a guess? I'm going to guess for the fridge 4 degrees Celsius. 4 degrees Celsius, that's my guess for the fridge. And for the freezer, I know that water freezes at 0 degrees, so I might put minus 5. So below 0, that's my guess. Okay, so we can take your thermometer and under the lead, and I'm going to open up the fridge and just put it on the glass shelf, and then close the fridge. And then the beauty is, because it's got a rubber seal and rubber's flexible, the lead can actually go through that seal. And so soon the temperature is going to start falling, and it's falling now. So I think it started at about 20 degrees Celsius in this room, and it's now at 12.7 and dropping rapidly. Now it will take some time it will take some time to equalise itself with the temperature in the fridge. Now what a fridge does to get cold is it doesn't actually make cold, it actually gets rid of heat. That's what a fridge does. So it takes, have a look, are you observant? It's actually got a temperature here, 5 degrees Celsius for the fridge, or it's just disappeared. I wonder if I press that button and minus 16. What a fridge does is it takes the heat inside the fridge and in a way it pumps the heat to the outside of the fridge. So you'll always find that around the outside of the fridge it's a little bit warmer than the rest of the room. Heat is a form of energy, and you can't destroy energy, but you can move energy from one place to another, and that's what the fridge does. It moves the heat from inside the fridge to outside of the fridge. It's not good to have a fridge in an enclosed cabinet because it's very difficult for it to then get rid of the heat, and so it works inefficiently. My fridge, it's got an unusual feature, and that underneath the fridge there's some big pipes, air pipes, that actually go to underground the house, and it actually allows cold air from under the house to come up and help surround the fridge, and that actually helps the fridge stay cold. So I'm at 6.1 degrees Celsius and still falling. Certainly does take a bit of time for it to happen. So we might have a little bit of a break for a moment, and I'll just wait. So I'll see you in a minute or two. Okay, so it looks like the temperature has stopped falling, and mine's at 5.6 degrees Celsius. Okay, 5.6 degrees Celsius. I wonder if there's a place on Earth that you know that would reach 5.6 degrees Celsius. Certainly, where it snows, in the desert, those places. But there's lots of places that will reach 5.6 degrees Celsius. Let's have a look at the freezer. Pop that there. Okay, let's let that stabilise for a little bit. Okay, well, that's chilly. -9 degrees Celsius. -9 degrees Celsius. Okay, let's go to the studio and we'll do a column graph of this data. Let's go. All right, now that we know the temperature inside the fridge and the freezer, it's a really good idea to graph it so that it's very visual. Okay, it's very, very visual. And I might include on this column graph the temperature in the kitchen so that it gives a fair idea of how the temperatures compare. So whenever we do a graph, start with the title. So we might put temperature in kitchen, okay? And that will include the fridge and the freezer. And so let's do the room. Okay, so we'll do the kitchen, the room itself. Kitchen. And let's do the fridge. And let's do the freezer. There we go. So we're going to record 3 graphs, or three examples. And then on the y-axis, or the vertical, we're going to put the temperature. Like this. In degrees Celsius. And whenever I do a graph, I like to try and use most of the space that I've got. I don't like to have a little tiny graph down here. So I'm actually going to start at, I'm going to put 0 here. I'm going to put 0 here. 5, 10, 15, 20, 25. I'm going to go up by 5s. So 5, 10, 15, 20, 25. Now, under 0, below 0, it's actually a negative number. So I'll go -5, -10. So the kitchen temperature was 20 degrees Celsius. So I'm going to draw a line at the 20. And I can actually hash that in there like that. And to make it even better, I can even highlight the full column, so that's very clear, very visual, very important. Beautiful. Now the fridge had a temperature of 5.6 degrees Celsius. So that was, here's the fridge, there's the 5. 5.6 is built between 5 and 6, and so that, and I might do a slightly different colour. You could use 3 different colours if you wanted to. And we'll go up about there and go across and do the edges. Whoa, not easy doing it like this. Hopefully you'll find it a bit easier to do. And I can hash it like that. And I'm looking at it thinking, you know what, I might actually make a little bit of a difference. I'm going to do a little bit of a difference. What I'm actually going to do to make it more visual is I'm actually going to, I'm just using a solvent here. Okay, I'm doing a little bit of a change. I think this will work better. I think this will visualize things better. I'm sure you'll agree in a moment. You'll see what I'm doing in a moment. Yeah. Okay, there we go. You'll see. And the freezer was -9 degrees. So what I'm going to do is I'm going to actually drop down from the 0. Zoop! There we go. I think that is much, much better. There. Absolutely. And you could even write kitchen, fridge. I think I'll do that. So I'm going to get rid of those labels there. And I'll put, you know, the kitchen here. Kitchen, fridge, freezer. I think that really highlights the temperature in relation to 0. And 0 degrees Celsius is the temperature at which ice freezes. So when you pull an ice cube out of a freezer, although it froze at 0 degrees Celsius, it actually, the ice cube is probably like at -9 degrees Celsius. You can get ice cubes that are colder than 0. Just because it freezes at 0 doesn't mean it is 0 degrees Celsius. You can cool down ice down all the way down to absolute 0, which is -273 degrees Celsius. Anyway, very interesting. And let's continue on. So let's now continue exploring temperature. And I've got my 16 ice cubes here. And I'm going to put 4, just 4, whoa, there goes one, 4 of the ice cubes into the beaker, like that. So I've got 4 ice cubes in the beaker. And I'm going to put in the probe and see whether I can measure the temperature of like those ice cubes. Now, it's not actually that easy to do because it's actually difficult to get the ice touching the entire probe. Now, because there's gaps and air gaps and that sort of thing. So it's actually it's not an actually easy thing to do, but I can see the temperature plunging, which is really good. And it's at 1 degree Celsius. So actually I'm fairly happy. I'm actually a little bit surprised. See how I'm holding it like at an angle, and I've got the whole 2 ice cubes touching the side of the probe, and I'm at 0.8 degrees. So in actual fact, I'm quite happy with that. So I'm going to call the temperature of the ice cubes. Now, I know that ice freezes at 0, so technically it should be less than 0, but, you know, 0.8, close enough. Oh, it's going down more, 0.7, 0.6. Oh, 0.7. Okay, I'm just going to call it 0.6 degrees. So let me write down the original temperature of the ice, 0.6, and it says temperature with salt. I'm going to add salt. All right, so here we go, a couple of spoons of salt. Now you could grind it in. Whoa, whoa, whoa! That was way too much. Way too much. Oh dear. Would have been better for me to grind it in. Anyway, there's plenty of salt there, and I'm just going to mix it around a little bit with the... Whoa! Straight away, look, there's a negative there. That's not 1.9 degrees Celsius. That is, whoa, negative 2.8. Negative 3.6, negative 4.3. The temperature is crashing. And I might, negative 5.2. Whoa. So I might just even move the negative 7.1. Wow, negative 8.1. So by adding salt, the temperature has plunged. Negative 9.2. That's incredible. I actually didn't expect that massive plunge to happen. Very surprising. Now it's sort of warming up a bit. So it went down to negative 9.2. So the temperature with the salt, negative 9.2. Very interesting. But the question is, well, does that same effect happen with like other substances, like say sugar? So what I'll do is I'm going to just rinse out my salty water, because I'd like to start with the same conditions. Okay, so when you do an experiment, you want to try and start with the same conditions each time. So, all right, so there we go. I've got a nice clean beaker, and remember I put in 4 ice cubes, and 4. And this time, what's the original temperature? Look, it will be very, very similar, won't it? I mean, okay, yes, they are melting a little bit. Probably should have go pop this back in the freezer so that it doesn't melt for this lesson. So you need to go put it in, get it out, put it in, get it out, put it in, get it out. Okay? So, yeah, I need to do that. And so the original temperature is 0.7 degrees, so very, very similar. And now I'm going to add a couple of spoons of sugar. Will this do? Will the temperature crash like when I add it? So I'm going to put in 3 spoons, and I'm going to give it a bit of a stir. Let's see if the temperature drops with the sugar like it did with the salt. This is called an experiment. We're doing a test. We're finding out the results and answering a question. And 1.3, certainly not crashing. Definitely not crashing. It's almost the same, 1.2. Oh, it is going down a little bit, 1.1. Now that could be because the ice is melting and the liquid is actually covering the probe a bit more, so that it's actually just reporting the temperature a little bit more accurately. So I'm at 0.6. If it goes under 0.6, it is 0.5, 0.4. So 0.3, I'm going to say that adding sugar does reduce the temperature a little bit, but not as dramatic as the salt. So I'm at 0.2, 0.1. Give it a bit of a wiggle, bit of a shake. Will it go down to 0? No, it's going back up now. So I'm going to go 0.1. Interesting. 0.1. So a small reduction in temperature. Now, what about citric acid? Citric acid, will that have the same effect as the salt, or will it have negligible effect like the sugar? I'm going to take a guess here. I'm going to make a prediction. You know, I've never actually done this myself. This is the first time I've actually done citric acid, and I'm not lying to you here. I've been a science teacher for 25 years and I've never done this before. There's always so much to discover in the scientific field. So 4 ice cubes. In you go. 1, 2, 3, 4. Put in the probe. I'm expecting it to go down pretty quickly. Probably down to about the 1/2 degree, something like that. While that's doing it, I'll get my citric acid at the ready. Okay, so we're at 1.7, 1.3. I'm getting some good coverage on this probe, so that's good. 1.1, 1, and okay, it's gone up to 1.1, so now's the time. In goes the citric acid. Fairly liberal amount. Now, I'm just thinking to myself, for this to have been a totally fair experiment, I should have done equal amounts of each substance that I'm adding. Like I should have said, add 4 spoonfuls each time. So there we go. There's an improvement that I can do to the experiment. Add 4 spoons each time. I'm going to actually fix the worksheet. I'm going to add that to the worksheet, so that the worksheet that you're looking at is going to be updated than the worksheet I'm looking at. And I'm not overly surprised, because I had a prediction and we are actually heading in the negative territory. So, is it going to be as dramatic as the salt? Well, one of the problems was, remember when I added the salt and I tipped in way too much? So that means it's not particularly fair. But you are doing it correctly. You are doing a fair experiment. So your results will be better than mine. Okay? Well, they'll be more valid. Your results will be more valid than mine. But mine are heading down to negative 1. So I'm going to write -1. So I started at about, I think, 0.7, and I went down to -1 degree Celsius. Okay, and then for the final one, I'm going to add bicarb, okay, bicarb soda, to my 4 ice cubes. So 4 ice cubes with 4 spoons. There we go. That's how we're going to do a fair experiment. Have the same starting conditions, but only changing one thing. What are we changing? The number of the ice cubes? No. The amount of the substance we're adding? No. The type of substance we're adding. Okay, now I'm going to cheat a little bit because I have got another. Whoop, there we go. There's 4 ice cubes. And just throw that one over there. It will melt. 4 spoons of bicarb. I might even just pop some bicarb in a beaker. That way I can scoop it out easy. Here we go. So 1, 2, 3, 4. Okay, I've made a little assumption, and that is that the temperature of the ice cubes will be the same each time. And so I didn't bother checking, but I probably should have checked. obviously you being the fantastic student, fantastic scientist, are going to be checking that. Yep. So, will it go colder than 0? I think it's sort of gone, it's gone like white and slushy here. Yeah, white and slushy. You're at half a degree, 0.3 degree. Oh, gone into the negative, 0.1. So yes, bicarb is having a similar effect as the citric acid. It is lowering the temperature. Okay, lowering the temperature. And oh, we're going back up to 0. Oh, not minus 0.2, minus 0.4. So the answer is minus 0.5. I'll go to minus 0.5. So start at 0.7 again, minus 0.5. Yes, bicarb lowers the temperature, but not nearly as significant as the salt. So if I want to drop something's temperature, I am going to use salt. Okay, I'm going to use salt. And so how about we do a column graph of those results? Very straightforward. We've been having some good practices of doing some column graphs, so it shouldn't be very tricky for us. Just tidy up our equipment, of course. Just sort of wipe up. You know, the more we can clean up, the happier everybody will be it your parents or the teachers, whoever. So let's pop this down here. Now, you might be wondering, why don't those lines disappear? Why don't those lines disappear? Did I use a different colour texture? Like, did I use a Sharpie or something like that? But they're very, very fine lines, aren't they? No. I wonder if you can guess how I made those lines in that laminate. I used a laser cutter. Yeah, I love laser cutters. Definitely my favourite pieces of equipment, laser cutters. Can do a lot with them. So, just blowing off the solvent. Excellent. And so, what have we got? The temperature of ice with different substances. Temp, ice with different substances. And it looks like I'm going to set the 0 line about here. So I might even draw a line across to the 0 so that we can see it clearly. And we had let's go, ice, salt. I'm writing small here, aren't I? What was next? Sugar. Citric acid. And then bicarb. Now, one of the reasons it's not coming up so well is it's still got some of that solvent on there. Okay. And we have the temperature. Temperature in degrees Celsius. And this was 0. Now the maximum temperature was only 6, so and the 0.6, and the lowest went down to 9. So, what do we got? 2.5, 5, 7.5, 9. I might go down up by 3s. A little bit unusual for me. -3, -6, -9. I normally like to have whole numbers, so that will make that 3. And the ice temperature was about 0.6 degrees Celsius. So the ice started off about here. And then the salt got all the way down to -9.2. Yeah, that's right. That's where the salt went. The salt went all the way down there. The sugar, the sugar barely moved. The sugar barely moved. Whereas the citric acid, it went down to 1, which is about here. and the bicarb went down only to about -0.5 degree. So there we go. We can see that it's quite dramatic by using salt. Adding salt to the ice, the temperature reduced dramatically, didn't it? Whoa! Look at that. So, and then after this next little segment, I'm going to show you something really fun you can do with this principle. I'm going to make some ice cream in a bag. So I've got an experiment for you to think about and to do by planning it, writing an aim and a method, and then actually carrying it out yourself. And the question is, does the temperature of water in a beaker change when you stir it? Okay, does the temperature in a beaker change when you stir it? So the aim would be like to find out if temperature changes when stirring water. How would you do it? Well, you'd find out the original temperature of the water by measuring it. Then you'd stir it quite vigorously, get a nice vortex, maybe for 1 minute or 2 minutes or something like that, and then measuring the new temperature. And then starting again and trying it again and collecting, maybe doing it 3 times so that you've got 3 sets of results. To make this a fair experiment though, there's something very important you need to do. Because remember, you'll be holding the beaker with one of your hands. Now if you're holding the beaker, where's the heat from your fingers going? Well, it will go into the water. So if the temperature goes up, you don't know whether it's going up because you're holding it or because of the stirring action, or both. So I suggest you get some little foam, something like padding, some insulation, so that you can insulate the heat from your fingers from the glass, so that even paper, a couple of layers of paper, or even a dry cloth, just so that your fingers are not putting direct contact on the glass, because otherwise it's not a very, very fair experiment. So on a separate piece of paper, you can actually carry out that experiment yourself and find out the answer. And if you do find out the answer, if you ever see me in real life, you can come up to me and say, Jacob, I did the experiment where I stirred the water and the temperature went... Well, you can tell me what you found, okay? And we'll be excited together. All right, so one last thing, ice cream in a bag. And hey, time for a special treat. We're going to make ice cream in a bag. So, going to need 2 Ziploc bags, a small one and a larger one. For the ice cream itself, we're going to need some cream. So this is thickened cream, some sugar, and a bit of vanilla essence. And then to freeze the mixture, we need ice and some salt. So let's make the ice cream first. So that we don't get confused. So in this little bag, we're going to put the ice cream mixture. Now, I think I've got, probably about 50 ml. The secret to this is to not make too much. It's better to do smaller batches than one big batch, okay? So I'll just double check to make sure. Yeah, that is sugar. It's probably not the best way to check things out in science. Okay, a bit of sugar. All right, and a little bit of vanilla essence. The essence of the vanilla. Normal vanilla. Oh, vanilla comes from the vanilla bean, which is actually quite expensive. So scientists have artificially, here we go, have artificially produced the chemical that tastes like vanilla, and that's called vanilla essence, and that's why it's so cheap. But it's basically just a synthetic or man-made manufactured chemical. So mixy, and this will dissolve the sugar a little bit. This will dissolve the sugar just a tad. And let's pop this ice cream mix into the baggie. Here we go. Now again, remember what I said? It's better to have a little bit than a lot. So there we go. The thinner you've got it in the bag, the more surface area there is for it to cool down. That's the secret. And next, we need the freezing mixture. So we need some ice. 1 lot. 2 lot. And let's pop this in the bag. Now, you know what? It's probably best, it would be best if you could crush this ice up. I'm sure it would be best. Crush it up either in a, like using a mortar and pestle, or covering it in a tea towel and like melting it, or even possibly even putting it in a blender. And then we're going to add some salt, okay? Because remember what the salt does? The salt will cause that ice to really lower in temperature, okay? So I'm just going to mix it through like this. Mix it through. And then make sure your Ziploc bag is sealed really well, because we don't want to get the salty ice into your ice cream, because maybe salty ice cream doesn't taste the best. Although I must admit I haven't tried it. And I'm actually of Dutch heritage. So both my parents were actually born in Holland, the Netherlands. And a lolly or confectionery that I've grown up to love, you won't believe it, it's actually salty licorice. Yes, if you've got any Dutch friends, they actually will probably like eating salty licorice. I know that is strange. It's black, salty licorice. Yum. My mouth starts watering just thinking about it. And now I've only got ice on at the moment one side of the ice cream. See that? See, there's no... And so that's probably not the smartest thing to do, is it? It's probably best to have a bit of ice on both sides. That would make sense, wouldn't it? So somehow I have to try and manipulate. I have to try and manipulate the salty ice to go on the other side. I think I'm sort of getting there. Okay, because it's sort of, wait, it is sort of melting a little bit. That ice. Oh, I hope it's not going into my ice cream. Now this is not, whoa, this is super cold. Oh, yeah, my hands are super cold. I'm going to put it like that. Now that's not how they make ice cream in Australian factories, but in India I've seen videos of where they have this steel metal drum and they fill it up with ice and they put salt in, and then they put the drum horizontally. They turn the drum and then they pour on it the cream, and they put the fruit on it, and they put the sweeteners on it, and it actually freezes on the drum. You should check that out. It's a special... Hey! Hello! Something special is happening here. Or another example I've seen is, again in India, is they have these trays of ice, and then they put salt in, and then they put like ice cream molds, and then they pour in the liquid ice cream, and after half an hour it freezes, and they, like street vendors. Check it out on YouTube. Very interesting. Okay, very interesting. And you won't believe it, but I've been gas bagging, and very excitingly, I've got ice cream. Look. Yes, open it up to reveal the contents. It's solid. I need a spoon. I'll use my finger. Okay. Oh, look at that. Oh, delicious. Not very nutritious. Something's tasting a bit salty somewhere. Not bad. Anyway, hopefully you've enjoyed the lesson as much as I've enjoyed the lesson, and I look forward to seeing you again soon. Bye for now. Hey, 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 we are looking at amazing water and surface tension, part 1. So, for this lesson, you're going to need a glass of water. Why are there bubbles in my water? That's interesting. Your food colouring, your junior chemistry set 1, the square stainless steel pan that comes separate to the set, and a 20-cent coin. Now, a 20-cent coin, that's important. Not a 10-cent coin, not a $2 coin, a 20-cent coin. And so we're going to be looking at something called surface tension. And tension, the word tension means to pull something. And sometimes when you pull something, something else pulls back. And the first thing you're going to need is the white plate. Okay, so the little resin plate. We'll pop that there. And you can get a beaker out and the pipette. That's it. And so mostly fill up the beaker, and hopefully it will be nice and clean. Because if it's not clean, then you might have some issues with this activity. And what's very interesting is we'll often use detergent to clean our glasses and that sort of thing. Well, detergent in this experiment is not our friend. So if you have used detergent, make sure you rinse it off really quite well. Okay, I assure you, detergent is not our friend. Now, what colour am I going to use? You can use whatever colour you like. I'm going to start with red and see if you can do a drop. Yay! Oh, I love it. And I can see the colour diffusing fairly quickly through that water, and that's probably because it's just been mixed. I might even do one more drop. Zoop! There we go. Lovely. Now, it's competition time. Who can put the most drops of water onto that resin plate just prior to the water running off? So I'm going to draw up a pipette full of water, and it's drop by drop, and you have to count. So I'll do it, but you can do it as well. If my counting disturbs you, then maybe turn the sound down. But I have to count out loud, otherwise I'll forget where I'm up to. And you also need to do it quite quickly, otherwise you'll be here forever. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. So far, so good. How are you going? I can see a little bit of a bulge, but I'm still nowhere near the top edge yet, so a long way to go. 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100. Okay. Now, I've got quite a bulge happening there. It's above the surface, but it's a little bit interesting. It's not like on the edge. Anyway, I'm at 100. What about you? Did you think you'd be able to get 100 drops on there? 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, 121, 122, 123, 124, 25, 26, 20. 125. 125. How did you go? How did you go? Or are you still going? 125. The white resin plate, I was able to get 125 drops on. So record it in your table straight away. And look, you could repeat that if you wanted to and find an average, but I will continue on. The round steel pan. The round steel pan, that's the one that's magnetic, remember? Okay, so the steel pan is the magnetic one, the one that will be attracted to the magnet. I don't need to test it because I can tell it's much silvery than the other round one. What's your prediction? How many drops do you predict that you could get into this one? Like, the diameter is less, but the sides are higher. So although it's got a smaller area, the height is larger, and so that would mean that the volume goes up as the height goes up. So I'm going to predict 100. What did I have last time? 125. I think 125. I'm going to do. That's going to be my prediction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81. Whew. If anything, this lesson will help you count. 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100! Whoa! Whoa! It's getting quite the bulge on top. See, surface tension is a force that's actually pulling the water drops together to form a skin. 101, 102, 103, 104. Oh! 103. 103. That was well under my prediction. Okay, I got 103. Are you able to beat me? Are you able to get more on there? Okay. And now I need the aluminium pan. And I might, you know what I might do? I might actually just and then squirt it. Vacuum clean up the water. Now I'm not sucking it up. That's the wrong word to use. It's quite complicated how it actually goes up. It's to do with air pressure around us and volume and all sorts of things. But what it is not sucking up the water. Okay. So just to be clear on that. So just wipe him down. Perfect. Oh, I love it. And there we go. It's nice to clean up as you go along. Excellent. And so now for the final one, the aluminium dish. And again, let's make a prediction. It's about the same diameter, but the height is a lot lower. So I'd say the volume is a lot smaller. So I'm going to guess 75. That's my prediction, 75. What about you? What's your prediction? And let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70. Whoa! So there's 70. I'm close to my 75. Notice that dome. Why doesn't it run off? Why doesn't the water run off? It's because the water molecules are attracting to each other and pulling themselves in. And that pulling in is called surface tension, and it creates somewhat of a skin on the surface. 71, 72, 73, 74, 75, 76. I'm past my prediction. 77, 78, 79, 80, 81, 82, 83, 84, 85. Whoa. 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96. 95. Oh, it was still less than the steel pan. It was still less, but it was more than I thought. It was more than I thought. So let's just record that. 95. Very interesting. And if you've got a 20-cent piece, maybe we can have another competition. You can load up the 20-cent piece with the most drops. Now, do you know why I chose the 20-cent piece? Why did I choose it? Because it's got a wonderful Australian animal on it, absolutely spectacular Australian animal, called the platypus, which lives mostly in water. It can traverse across the ground, but it lives mainly in water. And when the English first found it and sent one back to England, well, they sent a dead one, sadly. It was like a stuffed one called taxidermy. The people in England thought they were getting a joke played on them. They thought it was actually a few different animals that had been like stitched together, like the bill of a duck, the body of like a beaver, feet like, it's even got, they've got like the back feet have got spurs, and have even got like little poisoned little, incredible. The platypus is an incredible Australian animal. I love it so much. Beautifully designed, that platypus. Love it. Anyway, let's see how many drops we can pop on him. I should use blue water, shouldn't I? Enough of this red water. Let's go with some blue water, because it's, it's a platypus. It likes to swim in unpolluted water, which reminds me of something, and that is that, platypus do live in creeks and streams, and some places are lucky enough to have them in their local creeks and streams. And, if you put a lot of fertilizer onto your lawns, or there's a lot of dog poo, or, you wash your car and all the soap goes down the drain, well, that drain goes somewhere. That drain goes into the local waterway. And that will actually pollute it, and it might make it uninhabitable for the platypuses, or the platypi, I should say. And so we do need to be careful about what ends up in our local streams and waterways, particularly like rubbish as well. There was a poor platypus in Tasmania near Hobart, I believe. It had sort of got into this round plastic ring, and it virtually killed it. So that was really, really sad. All right, let's see how many drops of blue water I can put on Mr. Platypus. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. Whoa! And that doesn't really even have, it's got a slight rim on it, but 51, 52, 53, 54, 55, 50, 54. I got 54. What about you? What about you? And if you haven't quite had enough of doing this surface tension business and the drops of water, there's one more I'd like us to do together, and that is to make a beautiful gem. Make a beautiful gemstone. Now, that's why I've given you the square little pan. And notice I'm doing a little bit of cleanup here. Beautiful. Put the disc of wood in. The first thing, make a beautiful colour with your water, something special, and that with your food colouring in your water. And that might mean you might need to add some different food colourings together, different colours, and see what happens. I'd like to sort of make a little bit of maybe a purple. Give it a little bit of a mix here. Bit more blue. Yeah, that's not really purple. Okay. What about if I add a drop of yellow? Will that change? I know if I add the red, the blue, the green, and the yellow, I'll end up with black. So you don't want to just like go madly adding the colours, otherwise you'll end up with a black. Anyway, so here's the big question. What's different between this shape and the other shapes? It's a square. So what does that mean for the surface tension and the shape of the water that will go onto it? You know, like, will I get a domed effect but it's got corners? Interesting. Now for this one you don't have to count. You don't have to count. I'm just going to squirt my water straight on. So here we go, squirt, because I'm very interested to find out what the final shape will be. Okay, what will the final shape be? And I don't need a close-up of this because you should be doing this yourselves. Okay, this series of video lessons is not for like just to watch. You need to get the equipment. If you don't have the equipment, oh dear. Maybe we should try and organise that you can borrow this equipment from the local library. How good would that be? You know, people who can't afford the chemistry set can go to the local library and borrow it. Now that would be wonderful. Oh! Actually, I didn't want to load it up so much. Maybe I can put some more back in to try and build up the shape. Yeah, it's like a giant pillow. Absolutely beautiful giant pillow. Heh, love it. Okay. So, now what shape is a drop? What shape is a drop? Have you ever thought about what shape a drop is? What shape is a drop? Well, it's round, isn't it? If you were to do a squirt of a drop out in space, do you know what shape it would sort of like leave? Or if you're on the International Space Station, which is in constant freefall, I can tell you that it would be a round sphere. The drop would form a round sphere. Why is that? I mean, why isn't it a cube like a dice or something, you know? Why does it turn out to be a round sphere? Well, I've got something to show you and talk about. And I've got a little paddock. See this? And it's got a little sheep on here, and you might recognize that sheep from Minecraft. Yep, there we go. So let's say that you had a pet sheep and you had a paddock, but when you came inside to do your science, the sheep would walk away and escape. So you need to build a fence. Okay, you need to build a fence. So you go hunting around, or you dig up some copper and you make a copper fence. Yeah, this is actually copper wire. This is actually a copper fence. Most fences are not copper, I can tell you. They're made out of iron. So you make a roll. You make yourself a roll of fencing. So you've managed to make yourself a roll of fencing, and so that you can build a fence for your sheep for when you do science. But the science lessons can go on a little bit long sometimes, can't they? And so you need to have the paddock as big as possible for the sheep so it doesn't run out of food. So the question is, what shape are you going to make your fence? And there's three possible, I've given you a bit of, you could draw three different fences. I don't know, a square one? Is a square one the best shape? What about a hexagon? What about a triangle? Or what about another shape? What are some of you yelling out at me? Let's try a square. I'll fold that in half and then fold it in half again. Then I've got 4 equal sides. One side's bent the wrong way though, so that's not very good. Whoa! And so I'm making a square fence. There we go. Is the square fence going to be the best shape? Well, you know what I could actually do? Like, I could actually count how many little, little pegs there are. That would give me an indication of the area. See that? The more pegs within the size of that fence, the bigger the area. So you could actually count them out. Well, I'll tell you what the optimum shape is. The optimum shape, and I can't really do it now, but it's a circle. Yes, believe it or not, the optimum shape, the shape that will give the biggest area, the biggest surface area for the smallest perimeter, is actually a round paddock. Believe it or not, is actually a round paddock. So you could even count all those pegs and you'll see that there are going to be a few more than the square one. And that is why a drop is spherical, because a sphere and a circle, a sphere is basically the three-dimensional version of the circle. Because all the water molecules are pulling in on themselves, they pull in to produce the smallest surface area. And the smallest surface area of all the shapes is a sphere. There you go. Now you know. So, woo, thanks for joining me, and I look forward to seeing you next lesson. Bye for now. Hey everybody, we are doing surface tension part 2. And for this lesson, you're going to require a few little extras. So you're going to need some dishwashing liquid. Now, the brand and the type doesn't really matter, so just a little bit. I'm just going to put it in that little bowl. You need some full cream milk. Full cream milk, that's fairly important. Skim milk won't cut it. Almond milk certainly won't cut it, nor would coconut milk. From the cow, ooh, full cream milk. And some cotton buds, not to clean your ears, but for dipping into the, you'll see, milk after. So we're going to start with some swirly, milky patterns. Swirly, milky patterns. And we'll get the white dish out. And let's put the white dish there. And going to fill it up with the milk. Okay, now it's white on white, so it's going to be a little bit difficult to see. Now I think your teachers and your folks are going to love this one, because typically when this experiment or activity is done, people use like bulk amounts of milk and stuff, whereas with Tiny Science Lab you only need tiny little amounts, and of course you need some food colorings. So you can experiment yourself, but I'm going to put maybe 3 drops of food coloring in a blue one. Now the effect that we're going to see is definitely partly due to surface tension, but it's also due to the interaction of the food color and the milk and the detergent, mainly the milk and the detergent. The milk and detergent are going to do some very interesting things. Milk is quite interesting because it's a mixture of like water and fat globules. And detergent's interesting because it's a molecule that likes, it's a long molecule, and one end of it likes water and one end of it likes detergent, or is attracted to detergent. So quite complicated. Anyway, I'm going to dip my little bud into the detergent, and you know what? I wonder if I dip the part without the detergent in, see what happens. It attracts the water up. Oh, look at that. It colours the bud yellow, red and blue. That's not a great surprise. What about if I put in the detergent? Whoa! What about if I do some over here. It appears to push. It appears to push the colours away from itself. I can do a little bit of a swirl. Now we know why it's called swirly whirly milk artwork. Oh, that's getting a little bit dark now. I don't really like that very much. You can tip that out. You can do another one. Okay, you could tip that out and do another one. You can explore and investigate and see if you can work out what is actually going on. Because as I said, it is actually quite complicated. I might do one more myself actually. So let me draw this mess up. So I certainly wouldn't be entering it into an art competition. I think I've probably used too much food colouring there. That's my guess. I need to do some washing up. Ugh, milk. Milk can get a little bit coagulated and stinky over time, that's for sure. If I just drop it in and give it a bit of a wash. Wash the dishes, squirt, squirt. It's not washing as well as I would have liked. There we go. Okay, one more. Let's do one more. Squirt that out. Now, because I'm putting the pipette in the milk, you don't want to drink the milk after, okay? All right. I'm not filling it up as much this time. I might just do green and yellow this time. Or one drop of green. And one drop of yellow. Get my Q-tip, put it in the detergent. Ooh, all that really shot it apart, didn't it? Oh, that one's not nearly as good, is it? It's sort of, no, I think it needed a bit more depth. But anyway, that's what you find out when you experiment with things. You actually find out what works, what doesn't, okay? Trial new ideas, see what happens. What about if we did it in different size vessels? So I've got the plastic container there. What about a beaker? And what else do we need? A dish or a conical flask. Oh, it's going to be interesting. And a little middle dish. Okay, so let's have a look, shall we? Pour that there like so. Whoop, whoop. Who knows? I've never actually done this before. I've got no idea what's going to happen. Ooh, well, that one had a bit of red already in it. But I might actually see if I can... Notice when I put the cloth here, it actually absorbs the water by capillary action. Well, capillary action, well, the water absorbs up into the cloth and so it's used up. Okay. Let's do a drop of blue. 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 Now, because I'm doing a bit of an experiment, I might try and just sort of use the same colours in each one. That way, I'm sort of keeping the experiment a little bit fair. Does that make sense? The only thing I'm changing... Now, what's the question? You know, if you the experiment, what is the question? The question is, does the milky swirly artwork work in different vessels? And we're about to find out. Looks pretty good here. There. Does the color, are the colours pushed down or do they stay at surface level? I think they sort of stay at surface level. Not that impressive. This one here. Whoa. So I think you actually must get some interaction from the base of the pan somehow. I don't think anything's going to happen on this one. Nothing, absolutely nothing. You need obviously you need a bit of a surface area. What about here? Woo! That was quite good. Well, that almost seems like the perfect depth for it. Can do some swirls. How good's that? Very, very interesting. So we'll pop those to the side. A little bit like my works of art. I wonder whether those colours will diffuse through the milk over time. That one might be good to leave for overnight, a couple of hours, see what happens, the one in the conical flask. Who knows? And something very interesting too. Oh, I need some fresh water. I need some fresh water for this to work. Back in a moment. Now, this little demonstration I call Scaredy Cat Pepper. Scaredy Cat Pepper. And if I put just plain water on top of the surface of that plate, and then I crack a bit of pepper. Now, it might actually work better with finer pepper and sprinkle it on, to be honest. Like, oh, some of these chunks are probably a bit big. I don't know whether this will work or not. Well, that's what I'll find out. Now, I've got another Q-tip. Well, I'll put some detergent on it. And are we ready? I'm going to put the... Woo! See how it spreads out? The pepper spreads out. That must be because the detergent forms a thin layer on the surface and then travels outwards. So, very, very interesting. Detergent and soaps are very, very important to our day-to-day lives. Surprisingly, water is not actually very good at wetting things, believe it or not. Like, that is hard to believe, I know, but it's just true. So, for example, have a look at my blue shirt here, and I'm making it a little bit smooth, okay, because I'm going to get some water and I'm going to drop it on. Oh, see how it ran down about 10 centimeters before? Oh, that drop sort of ran off. Woo! See how the water's just like mostly running off? Well, some of it's soaking in, that's why it's going a bit darker blue here. But the water runs off. See that? The water runs off. However, if you put a bit of detergent in that water, it will not run off. I can guarantee you of that. So I might mix a little bit of detergent with the water, like this, and draw some up. And this time, if I put a drop of water on, you watch, none will run off. It will just go straight down, straight into the shirt. Might have to come here and do it on this side. I'm trying to get the shirt smooth. Here we go. And whoop, up, see? Only travelled 2 centimeters before it got soaked in. Do it again. Whoop, there we go. None of it runs off. It just totally gets soaked in. And so, Australian native plants, their leaves sometimes have tiny little hairs on them, and those little hairs stops water from leaving the leaves. And on a dry continent like Australia, that's very, very important. So how about we just go have a look at a few leaves around the place and squirt a bit of water on them and see whether the water runs off. So let's go for a little bit of a field trip. Okay, let's head off and see what we can see. Let's go. Okay, so we're in a bit of a dry rainforest, and this is the leaf of a bungalow palm. And what I'll do is let's drop some water on the leaf and see what happens. Woo! It runs off. The water runs off the leaf. Oh, it is wetting it a little bit. It is wetting it a little bit, but most of the water is running off. Here's let me pick it. The leaf of an arum lily, and woo! Look at that. The water just runs off that as well. Hey, well, the water is wetting it a little bit, but it's actually formed some nice big drops on the arum lily too. And those drops are circular. Oh, and look, we can load it up on the lily as well. Woo! Look at that, nice big drop. And run off. So good. What about, is there anything else in this little forest that I can show you? It's hug a tree kind of day. This tree is very special to me. Gives me a lot of hope. About 25 years ago, I left my first job as a teacher to go start at another school, and they gave me a small pot plant to say farewell. And I planted that pot plant in this rainforest, and 25 years later or so, it is a super high tree. I can't even film it for you because it's so high and the camera goes out of focus. But it gives me hope because it goes to show that, you know, mankind can be very destructive, but, you know, if we plant things and look after things, things can grow back. And that gives me a lot of hope. What about this awesome paperbark tree? I wonder what happens when we put water on the paper bark. Oh, it's stuck there to start with and then it ran off. Stuck there to start with and then ran off. Interesting. And Aboriginals used to use this paper bark to wrap their food in and put it into fires. You could also do big layers of it and it would float on water, and you could actually make a little bit of a raft out of it as well. That's what we used to do down in the creek. Big rafts of paper bark, and we used to sit on them and float down the creek. I love the forest. Anyway, that's it for this lesson. I'll look forward to seeing you in the next lesson. Bye for now. Hey everybody, welcome to another exciting science lesson. And we are looking at solubility today. So, for this lesson, you are going to need look at all this stuff. It's all very common and what you've probably got around, but you're going to need some salt, some sugar, some food colouring, citric acid, bicarbonate of soda, and some flour. Now, not the sort of flour that you give your mum, the sort of flour that you make cakes out of, and of course the junior chemistry set number 1. So let me just put some of this stuff to the side, and let me ask you a question. What do you like for breakfast? What do you like for breakfast? Well, I like cups of tea. Now, I don't normally make tea in a glass, but I am going to make tea in a glass in a moment. And I have tea with toast. Normally I have a plain white bread toast with Vegemite, and I'll have some fruit loaf with some brown sugar on it, believe it or not. My Dutch heritage means we actually put sugar on our bread. I know that sounds terrible and not very healthy, but sometimes we put white sugar on our bread. I don't do that very often, but I use a lot of brown sugar. Okay, don't judge me, please. Now, the tea I normally make in a mug, but I'm going to make it in a cup today. And I don't know, I've got this present. Normally I have tea bag tea. Dilmah is one of my favourite. But I don't know, somehow I got given, I don't know, maybe a hamper or something, and there was a box of normal tea, anyway, it's loose, what you'd call loose leaf tea. Now my wife hates it because I normally somehow manage to spill it everywhere, but I just didn't do it. I didn't spill then. So I've got some tea, and I'm doing it in a glass so that you can see it. So there's some loose leaf tea in the glass. And I'm actually surprised how long this has lasted. I wouldn't mind doing an investigation on the cost comparison between loose leaf tea and tea bags, because I actually think this could be a lot better value, and there's actually less wastage as well. So anyway, I also like to have a spoon of sugar with my tea. Not a loaded spoon, just like about, a teaspoon of sugar. And you add hot water to your tea, because even if you're having iced tea, I'm sure they start off with hot water, because there's something special about hot water, and that is that the particles of water are moving very, very fast, and they cause the dissolving to happen a lot faster. Then I give it a bit of a stir, and you might be thinking to yourself, doesn't he just drink a whole lot of bits of tea leaves and that sort of stuff? But the interesting thing is that most of the tea leaves sort of go, especially when I do a little bit of a vortex, most of them actually end down the bottom. Now, the water's gone brown. That indicates something sort of dissolved in it, okay? Now, the tea leaves themselves don't mainly dissolve. So they are what we call insoluble. The tea leaves are insoluble. But the sugar's all gone. I can't see the sugar. I can taste the sugar because it's sweet. So the sugar has dissolved. And so, I got a tea leaf. Yeah. Okay, all right. Makes me feel like I'm camping or something like this. There's a few tea leaves sticking around there, but that's okay. Bit of extra roughage in your food. So, but there are some chemicals in the tea leaves that I think dissolve, and that's what's causing the water to go brown. Now, I'd have to look at it under the microscope to actually see whether the brown is due to dissolving or whether the particles are really, really fine. I'm pretty sure it's dissolving. And so this lesson today is on asking a question. And the question is, does salt or sugar dissolve the quickest? Does sugar or salt dissolve the quickest? That's the experiment we're going to be doing. And so we're going to need a beaker. Going to need a beaker out, that's for sure. And definitely going to need the stirring rod, okay, because you're going to be stirring. Also need the spoon, like so. And so we're going to do the dissolving each time in 10 ml of water. Okay, so 10 ml of water in a beaker. So with an experiment, you need to keep everything the same except for one thing that you change. And the thing that we're going to be changing is whether we're dissolving sugar or salt. Okay, so this is actually, you'll see in a minute that this experiment is a little bit tricky to keep fair, and I'll tell you why that is in a moment. Well, it's easy to use the same beaker each time. It's easy to use 10 ml of water each time. It's easy to put in the same amount each time. What's not easy is stirring it at the same rate, because you always have to stir it at the same rate, and also making a decision when the time has ended, when you've decided that the sugar or the salt has dissolved. So, tiny spoon, and you need to get a level spoon of sugar. So I've just wiped it with the edge of the stirring rod, which is not a good idea really, because the stirring rod could be wet and we don't want to get any moisture with our spoon. So I might actually use like a pencil. There we go. So I've got a level spoon of sugar ready to go. And so let's just have a quick practice at stirring. You hold with one hand, the beaker with one hand, and you rotate quite fast without too much banging until you get a little bit of a whirlpool happening, or a vortex or a swirl. Now you'll see that the crystals of sugar will be down the bottom. Now occasionally you have to sort of bring in your stirring rod to the center to sort of like swish them apart, because otherwise they sit at the center of that whirlpool and they don't actually move very much. So you actually have to like sort of swish them apart, and also could take a very, very, very long time to get 100% dissolved. So we're actually aiming for only about 95% dissolved before we actually call it dissolved. Okay, so keep that in mind. We just need it mostly dissolved and disappeared. So bear that in mind. And what I'm going to do is I'm going to call out the times. So I'm actually going to do it by myself. I'm going to be doing it in front of you here, not by myself, because I'm with you, of course. I'm putting this on stopwatch. I'm not checking Facebook. Okay, just thought I'd let you know that. And I've got it like that. And so that you can watch, the sugar dissolving, I'm going to call out every 5 seconds. So you just listen out, all right? You just listen out for the times being called. Okay, are you ready to go? Have you got your 10 ml of water, your stirring rod, and your spoon of sugar? Give me a thumbs up. Okay, I see thumbs up. I don't really, but I'm pretending I am. And, okay, here we go. And ready, set, dump it in, press start, and I'm going to start stirring. So, that's 5 seconds. 10 seconds, 15, 20, 25, oh, it's almost there, 30, 35. For me, I'm going to call it 35. You could still be going though. So I'm going to 40 seconds. I'm going to keep going up to 60 seconds. 45. 50. 55. And 60. Okay, so jot down what your time was. Okay, jot down what your time was. There's a table, spoon number, the first spoon was sugar for me, and it was 35. Now I don't write down 35 seconds because I've actually got the seconds up in the heading here. And we're going to do this a total of 4 times for each substance. Now, the most scientific and the best way to do it would be to tip this out and start with fresh water, 100%. That would be the best and most scientific way of doing it. However, we actually want some sweet water for the next bit, and I can tell you now that by having this at a little bit sweet is actually not going to make any difference to the time of dissolving, because sugar actually water dissolves a lot of sugar, so it's not really going to affect it. But if you're absolutely pedantic and you're absolutely desperate to do this fully correct, then tip that out, rinse it out, and start with fresh water. That's okay. You're allowed to do that. I just won't. But I do recognise, and I know some teachers are going, that is not very scientific, and that is not a fair experiment. I understand that, but that's how I'm going to do it. My apologies to you if I'm causing you too much angst. Okay, are we ready? And dump it in, press start. And so let's see how long this spoon takes to dissolve. It's very good to repeat experiments. And that's 10 seconds, 15 seconds, 20 seconds, 25 seconds. Oh, mine's pretty close now. 30 seconds, and 35. 40. Some of you are still going. 45. 50. 55. 60 seconds. Stop. Okay. So I'm actually going to put down 35 seconds again. Now, interestingly, I haven't mentioned anything to do with safety, but I do want to point something out to you, that there is actually a danger here. I wonder if you can see what the danger is. You might be saying, oh, maybe the broken glass or something. If that stirring rod was pointed this way, towards me, and I come down with my face like this, there is a danger that that gets poked right into your eye. So it's best not to leave your stirring rod in your beaker for a few reasons. Number one, if the stirring rod's in the beaker, will tip over quite easy, and two, the danger of your eyes. If you're wearing safety glasses, even better, then you won't have to worry so much about that. Okay, let's do the third spoon. Let's do the third spoon. And again, if you're very pedantic and you want to do this 100% scientifically, then tip out the water and start again, but I'm not. Okay, so I've got my spoon of sugar, level spoon of sugar. Same conditions, same amount of sugar, same amount of water, same beaker. And are we ready? Set. In it goes. Press start. And stirring. 5, 10, 15, 20, 25, 30. I'm actually going to call mine dissolved at 30. Yep. 30, 5, 40, 45, 50, 55, and 60. All right, so one last spoon. Now, you might be getting different times than I am, and there's a few reasons for that. Could be that you are stirring it at a different speed. Could be that your sugar is different than mine. So you might be using caster sugar, and the crystals are very, very small, which means there's a larger surface area, and they will dissolve more rapidly. Or you could be using like natural sugar, like really large raw sugar crystals, and they have a smaller surface area for their volume, and so they could take a long time. So there's a few factors for why you could be getting different results. It's not because you're wrong. Well, you might be wrong, but but it's probably because of those things I've just mentioned. And for our last spoon of sugar, and dump in the sugar, press start, and let's stir. Okay, it's very important to try and stir at the same rate. Okay, so that's not easy, is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I better call out the times, eh? 15 seconds. 20 seconds. 25 seconds. 30 seconds. 35. Okay, mine's done. 40. 45. 50. 55. And 60. All right. So now don't tip this out. Don't tip this out. What I want you to do is actually remove half of the water. We're going to do something a little bit different, before we do the salt. Okay, we're going to do something a little bit different before we do the salt. We're going to look at something called a diffusion layer. So I want you to draw out about half of this sugary liquid. Okay, and then we're going to make it even more sugary by adding a giant scoop of sugar. So just put in a giant scoop of sugar and dissolve that in. So we're getting a very, very sweet solution. Okay, so that's what we're after, a very sweet solution. Now there is a limit to how much sugar you can dissolve in so much water. Okay, there is a limit, and when you've reached that limit, that's actually called a saturated solution. Okay, a saturated solution. That means the water will not dissolve any more sugar at that temperature. And different substances have different amounts of saturation levels. So, you know, there's a certain amount of salt that you can dissolve in water. There's a certain amount of copper sulfate that you can dissolve in water. It's not the same. Now, the amount that you can dissolve actually depends on another thing as well, and that is the temperature of the water. If you increase the temperature of the water, you can actually dissolve more. Okay, you can dissolve more. Okay, so that's dissolved. That's a sweet solution. Just going to let it sit and relax and stop moving, like stop the swirling motion. And then going to do something that's a little bit tricky. You need fresh water, and I'm going to get my stirring rod. I'm just going to make sure it's clean. Okay. Now, this is a little bit tricky. You're going to put the stirring rod on the inside of the glass and just touch the inside of the glass there. And then I'm going to run fresh water down that watch glass. There, down that stirring rod, I should say, not watch glass. I'm very gently adding fresh water to this solution. Okay, very gently. So the water level is going up. Very unusual, isn't it? Okay, so now don't move it either. Don't pick it up and move it around. Okay, let's just let it sit there for a moment, and then I'm going to get some blue food colouring, and I'm going to put 1 drop of blue food colouring. What do you think is going to happen? It's very hard to predict. There's a drop. It's very interesting. There's another drop of red. Oh, this is fascinating. This, I was actually, I saw this when I was doing an online class, and I think a student showed me on the online class. Now I've been doing it a lot with a lot of different kids, because I love it so much. Look at that. Look at that. It's a little bit dark, but see how, like, there's a barrier. Like it seems like there's an invisible force field that's stopping the food colouring. In fact, it's like going whoop, 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 at that interface between the sugary water, which is very dense, is on the lower level, and the fresh water is sitting up the top, and it seems that the two don't mix at all. That is very interesting, isn't it? Oh, wow. And I meant if we were to leave that for some time. In fact, I will leave it for some time and see what happens. Okay, so I'm just going to put it to the side. And so, how about we continue with our experiment? And did I write down my final value? I didn't actually write down my final value, but it was actually about 35 seconds. And now we're going to do it. Whoa! Oh, sorry about that. Now we're going to do it for salt. Okay, so we're going to do it for salt. So I'm going to get out my other beaker because that one's being used, and I need, now it's virtually identical. Okay, it's virtually identical, which is important because in an experiment, as I've said, you only want to change one thing, and what we're changing is whether it's sugar or salt. There's a little acronym called COWS. COWS. See, cows out in the paddock, and cows. Oh yeah, I haven't quite said it the whole thing yet. Cows moo softly, so moo. Well, I've actually heard cows moo quite loudly, but cows mooing. Cows moo softly. Why am I telling you that cows moo softly? Because the word cow starts with C. So what are you going to change? What are you going to change in the experiment? And we're going to change to salt. We're going to change to salt. We started with sugar and now we're changing to salt. Moo starts with M. What are we going to measure? Well, we're actually going to measure the time it takes to dissolve. What are we measuring? The time it takes to dissolve. And softly, what are we going to keep the same? We're going to keep lots of things the same. We're going to keep the beaker the same, the fact that we're using water at the same temperature, the same volume. We're going to be stirring at the same rate. So lots of things to keep the same. So how do we remember the acronym for how to do a scientific experiment? Cows moo softly. Moo. Right, so I need some salt. Oh, this is a lot of salt. And make sure your spoon's dry. Mine's actually got a bit of sugar still in here, so I might just scrape the sugar out with the end of a spoon. Give it a blow, and try not to spit on it, of course, and I'm going to just dry it with the corner of my tablecloth. There we go. And how do I get the salt out easy? I might actually get this lid, and I'm going to pour my salt onto that lid. There we go. Oh. Okay. So I need a big full spoon of salt to put in. No, of course not. I need a level spoon of salt. It's got to be the same. All right, so let's get the stopwatch going. And ready? Everybody ready? 10 ml of water beaker. Tip that in, press start, and stirring. Try and stir at the same rate. 5 seconds. 10 seconds. Sometimes I'm going into the middle a little bit. 15 seconds. Whoa. It's disappearing. 20 seconds. 25 seconds. And mine was done at 25 seconds. There we go. 35. 40. This is for people who are still going. 45. 50. 55. And 60. Okay. All right. So for me, it was 25 seconds. I wonder what the time was for you. So 1 spoon of salt was 25 seconds. Okay, you can get your second spoon out. And we need a level spoon. Scoop him on and then scrape it off. There we go, level spoon. In it goes. Press start. Start stirring. Okay, stirring at the same rate. 5 seconds. 10 seconds. 15 seconds. 20 seconds. 25 seconds. 30 seconds. Mine's dissolved. 35. 40, 45, 50, 55, and 60. Okay, so that was a little bit longer for me, 30 seconds. What about for you? Let's get our next spoon ready. You're going to be a pro at stirring in a minute. Okay, stop, reset. In it goes, start, stir, 5, 10, 15, 20, 25, 30. Okay, mine's definitely dissolved. 35, 40, 45, 50, 55, and 60. Okay, so mine was 30 seconds again. Now, if you're using a giant piece of Himalayan rock salt, then you'll be stirring probably for the next half hour. So I probably should have said, don't use giant crystals because that just won't work very well. Okay, and our final one, which I'm glad you'll be happy about, our final spoon, and in it goes, and starting, and stirring, 5, 10, 15, 20, 25, 30, 35, 40, 45. Oh, mine finished. 50, 55, and 60. Now, I was totally distracted then. I was thinking about something else, I must admit. So, I'm actually not sure what time mine dissolved at. Okay, so I really apologise. So I'm actually just going to put a question mark there because I was thinking about a science lesson down the track in the future, and so I didn't realise what time it was, and so I'll just put a question mark. But it's okay. Sometimes you make a mistake or you write down the wrong thing, and then later on we can solve that with the. That's okay. We've just got to be honest about doing when we do science, and not write down things that we think we saw or things that we didn't see. Just be open and honest and transparent. If you make a mistake, you make a mistake. That's fine. Just own it. All right. I'm going to get rid of half of this water. I'm going to get rid of half this salty water. And we're going to, before we graph our results, we're going to do our diffusion layer. So half the water is gone, and I'm going to put in, remember, a big spoon of the substance. Okay, so an extra big spoon, and I'm going to stir that in. I'm going to quickly dissolve it. Now, just having a look at your results. For me, the salt dissolved quicker. probably about 5 to 10 seconds quicker. So that's actually pretty straightforward for me to say that the data suggests that salt dissolves quicker than sugar. That's what the data suggests. Or at least my salt dissolves faster than my sugar. Alright, so that's salt's dissolved. And remember, we need to get some fresh water. And I'm going to put the stirring rod on the edge, and I'm going to run water gently down into the beaker. Now the reason I'm doing it like this is so that the water goes in very, very gently without disturbing the water or the solution that's already there. Now what is the solution? The solution is the water that's got the salt dissolved in it. Okay? In this case, the water is what we call the solvent, and the salt is what we call the solute. So water is the solvent, the salt is the solute, and the salt water is the solution. So there we go. All right, now let's see whether this diffusion layers occurs with the salt. Now I'm going to start with red this time. I don't think it matters which color you start with. The reason I'm starting with red is that it's not as strong a color as the blue. And I can see again straight away that there seems to be some type of invisible force field. Look, that is very interesting. Very interesting. Look, how wonderful is that? Isn't that amazing? I didn't put in blue because I think the blue's too dark. The green's quite dark too. And so I've got two. Look, and there has been very little change over time, over the last 10 minutes. Very little change. Isn't that interesting, diffusion layers? Which then begs the question, and this is an experiment. This is an experiment that you can do, okay? And the experiment is, okay, we've done this mysterious diffusion layers with sugar. We've done it with salt. The question is, what would happen if would it do something similar with citric acid? Would it do something similar with bicarb soda? Would it do something similar with flour? Okay, so you know how to do it now. Remember, you have to get quite a concentrated solution in half the beaker, the bottom half of the beaker. You have to gently add fresh water using the stirring rod and the technique I showed you, and then you add the food colouring. So it's over to you, okay, to actually do that for yourself. I'm not going to do it with you. I've shown you the basic idea. You can do it. You've got the skills. Trust in yourself. Believe in yourself. Okay? All right. But our final thing today for this lesson is we're going to graph the results. We're going to graph the results. So whenever we do a graph, we always start with the title. And so we can put dissolving. Now, it's dissolving one S or two S's? Two S's. Check your spelling, people. Dissolving rate. Rate is how quickly something occurs. Of sugar and salt. And so, what do we put down along the horizontal or the x-axis? What do we actually put? We put the spoon number in this case. Okay, bit strange, but that's actually what we do. The spoon number. So spoon number 1, 2, 3, or 4. So I'm actually going to call this one here 0 spoons, 1 spoon, 2, 3, and 4. And here on the vertical or the y-axis, I'm going to put time. Now, some people say, shouldn't you put time on the bottom? No, it's actually sort of what you change goes on the horizontal, something what we call the independent variable, the thing that you actually change. And so our times, for me, well, you guys, I'm going to go up to should go up to 60 seconds because that's the time that I was allowing each time. 10, 20, 30, 40, 50, 60. That, okay. I really like to try and use the whole amount of the graph. 10, 20, 30. Okay, I'm going to go up by 10s. I'm going to go up by 10s. It's a little bit of a compromise, but I'm going to go up by 10s. There we go. And so for sugar, the first spoon took 35 seconds. So the first spoon took 35 seconds. And I'm going to put a nice big cross. Okay, a nice big cross there. The second spoon here, start here, going up. It also went to 35 seconds. The third spoon was 30 seconds. And the fourth spoon was 35 seconds. So it's a relatively straight line. Now, could do a bit of a dip, but in actual fact, I'm actually just going to go as, I actually think that that's a fairly fair line of best fit. You can argue with me, that's okay. I'm not going to dip down to the 35 seconds. I'm going to call it for that. And this is our sugar. So I'm labelling that line sugar. What about the salt? Well, I'm actually going to use a different colour texture. And so the salt, the first spoon was 25 seconds. And I'll put a cross there. Second spoon was 30 seconds. Third spoon, I put 30 seconds. Oh, they occupy the same spot. And my fourth spoon I don't have. So I'm actually, based on this, I'm actually going to do like that, and then I'm actually going to do a little bit of a curve. So different people will have different ideas about what this line of best fit will look like, and that's okay. And that's salt. But what it fairly clearly shows to me is that the sugar took longer to dissolve than the salt. So the salt dissolved faster than the sugar. Why is that? Why is that? Well, there's a few possible reasons, and that is that the crystal sizes of the sugar and the salt are different. In fact, the salt crystals were a little bit smaller, I could see that. But also the actual molecular arrangement of the sugar and the salt crystals is totally different. So there's actually totally different chemistry happening here as well within sugar and salt. So there's no reason chemically why they should dissolve at the same speed, that's for sure. Anyway, that's it for this lesson on dissolving and also looking at those diffusion layers. Hopefully you've enjoyed the lesson and you've learnt a little bit. Don't forget, cows moo softly, change, measure, keep the same. And I'll see you next time. Bye for now. Okay, everybody, we're up to exploring Orbeez. So for this lesson, you're going to need some salt and some sugar and some food colouring. So food colouring, and you'll also hopefully have put some Orbeez in a glass of water overnight. Now the Orbeez start off really, really small, like tiny, like 1 millimeter across. And if you leave them in water overnight, they end up, maybe, I don't know, that's about, each one of these is probably 6 or 7 millimeters across, something like that at a guess, maybe even 10 millimeters across. Now that doesn't mean that they've grown in size 10 times. No, because just because you double in your size doesn't mean you double your volume. So in fact, the volume of a sphere, I believe, is 4/3 pi, which is 3.14 approximately, times the radius cubed. So what that means is that if you double in size, well, then your radius doubles, but then it cubes. So if you go from, if you double in size, your volume goes up by a factor of 8. Okay, so it's not that straightforward. Now, are these dangerous? Now, the little tiny size, the maximum size it gets to is, you know, that. Now, if that size is going to block a baby's throat, yes, they're dangerous. And so you need to keep these away from little tiny kids. The ones that we send out are really, really small, and we don't believe that they're a hazard. However, there are other Orbeez available, and we don't send these ones out because they are a hazard. And the reason that they're a hazard is because they start off quite large. I can't even open this up. They start off quite large. Let me show you how large they start off. I'll just get a pair of scissors to... Oh no, I don't need that. I can pop them here on the table. This is how big they are before they start. If you put them in a glass of water overnight, they'll be as big as your hand. And so if a little kid was to swallow one of these and it gets stuck in their throat and then expands, then it will actually block their airways. And so the larger Orbeez are very dangerous. But I usually consider everything has safety issues and implications. So try and keep little kids away from everything. That's fair enough. Okay. So let's have a look. Let's do something very satisfactory. And if I get my Orbeez and if I get my tiny spoon out, let's pick up an Orbeez with the tiny... Ah, look at that. That is very satisfactory, isn't it? Oh, and it sort of gets stuck, doesn't it? Ha! Might pick up a different one. What about a nice pink one? It's like the perfect fit. And look at that. Very satisfactory. Now, why doesn't it fall out? And part of the reason is to do with air pressure. Well, a lot of the reason has to do with air pressure. Some of the reason has to do with surface tension. So, all right. What we're going to do is I'm looking at a little yellow one there, a little yellow Orbeez. And what I'd like to do is do a little bit of camouflaging. We're going to do the disappearing Orbeez. And so let's get some water in here, in this beaker. I might pop that there like that. And like this. Okay, so we've got 10 ml of water about. And I'm just going to get that little yellow one. I've got my eye on a yellow Orbeez, so I'm just going to get it out. Now it's very pale. It's a very pale Orbeez. So in the other beaker, I'm actually going to squirt some water and then add some food colouring to this water to dilute it. I'm diluting the food colouring so that I can then add some dilute. Oh, that was about right. Okay, yeah, I'm trying to match the two colours. So I'm going to add just a little bit more water to make that a little bit fainter. Very good. And if I put in a green... Oh, it's actually quite difficult. They really do get stuck, don't they? Especially if there's some water. Whoa! Wait, hang on. Let me put in a yellow one. Whoa! Whoa! Let me get some more yellow ones. Whoop! Another yellow one. Some of these colours are a little bit... Oh no, that wasn't a yellow one, that was an orange one. So I'll take that out. Or slightly pink. Come on. Whoa! Orbeez, Orbeez everywhere. I think you're yellow. Look at that. And it appears... Looks like they've disappeared. I can just see them. Can you just see that Orbeez? Like the water's overflowing. But then if I reach in, hey, I've got an Orbeez. So when you match the colour of the water to the Orbeez, then, oh, that one broke in half. No, that's not a problem. Okay. When you match the colour of the Orbeez, they disappear. Interesting, isn't it? So next, let's get to just some plain water. And here we go, there's some plain water. And I'm going to put in a blue Orbeez so that you can see it. And what does the blue Orbeez do? It sinks. Okay, the blue Orbeez sinks. Now what about if I get a bit more water and I actually add some salt? So I'm going to add some salt to this one. Maybe a couple of spoons like that. And stir it up. So dissolving the salt. Now if I add a other Orbeez, and I should get another blue one to match it, what do you think this one's going to do? Oh, no, it was a green Orbeez, but it's floating. So this Orbeez is sinking in fresh water. What are you thinking about? And this Orbeez is floating in the salt water. You might have heard of, I think it's the Dead Sea, where the rivers go in, but there's nowhere for the water to go out. And so as the water evaporates, the Dead Sea gets saltier and saltier, and you can when you lie in it, you don't just float in it, you like pop up to the top of the surface. That's because salty water is more denser. Salty water is more denser. Is that a word? I think so. What would happen if I started to squirt some of this salty water into the one that's not salty? See this? So I'm making this one here, saltier by adding some salt water. What will happen? Whoa! The Orbeez starts to rise. See that? Hey! And up it goes. So now I've made the water. Oh, it's sort of like, yeah, it is definitely, the water's definitely more dense than the Orbeez. I could actually though adjust the salinity so that the Orbeez is neutrally buoyant. Does that make sense? Woo! I could adjust the salinity so that the water is neutrally buoyant. I've got water going everywhere here. Very interesting. And so basically it just actually goes where you put it. So got to make sure it's stirred up and all the rest of it. So that's how we investigate different densities of different, what shall we say, solutions. Now, I'm about to do a activity that I thought up in my brain, and I wrote the instructions down in my brain. Well, I didn't write them in my brain, but I did it without actually doing the experiment. So probably not the smartest thing to do, but that's just me, I guess. And so what did I say? We're going to try and do different density layers. And so what did I write down? 5 spoons of sugar to 10 ml of water. Okay, so I need 10 ml of water. Now I've got to get some fresh water. Back in a moment. Okay, so I need 10 ml of water. That's good. And I need 5 spoons of sugar. 5 spoons of sugar. Now, I've got to make sure that my spoon is dry for this. Spoon is dry. And they sort of need to be equal size. I'm not going to do level ones. 1, 2, 3, 4, 5. Okay, 5 spoons of sugar, and I definitely need to dissolve it. Okay, now this should take about 30 seconds or something like that. So, or no, what did we do in a previous experiment? Should take, well, that was 1 spoon dissolving. I wonder, and this would be a very interesting thing to investigate. If 1 spoon of sugar takes 30 seconds to dissolve, does that mean 2 spoons of sugar take 6 minutes? 1 minute? Not 6 minutes, 60 seconds, 1 minute. Does that mean 3 spoons of sugar takes 1.5 minutes? Here's a question. If it takes 1 boat a month to travel around Australia, does that mean 2 boats only take half a month? Not sure if that's related or not. But okay, so there's 5 spoons of sugar. And what I need to do is I'm going to colour this red. Okay? Colour this red. Nice and dark colour. Alright, so that is red. And I need to put 2 ml of the red water into this beaker. So 2 ml. There we go. Perfect. Now, tip this out. Tip this out. Give it a little bit of a rinse to get rid of the red. And I need 10 ml of water. And this time I need 4 spoons of sugar. 4 spoons of sugar. So I'm making a solution. 1, 2, 3, 4. It's not as sweet. It's not as sweet. Okay? So I'm hoping that the density will be less. Now maybe I should have done this with salt. I probably should have done this with salt. I think this might work. If I did it with salt, the salt would actually dissolve faster. So there's another experiment you can do. If this doesn't work, if this experiment doesn't work with the sugar, you can try and do it with the salt. Or even if it does work with the sugar, you can see whether it works even better with the salt. Okay? So, always thinking of things to experiment. Okay, what colour do we need to add? Green. Has that dissolved? Yeah. So let's go green. And we'd like to have a nice colour. That's not bad, is it? Okay. All right. Will this work? I've got no idea. I'm so nervous now. I'm going to bring it up. I'm going to put the stirring rod on the edge and I'm going to dribble green down into this. Will it form a layer or will it just mix? Something. Oh! I'm seeing a little bit of a layer. I am seeing a bit of a layer. I'm actually going to make this a bit greener. A little bit darker. I actually think it is forming a layer. I'm not joking. I'm in a little bit of shock here. I've got a feeling that this may actually be working. No. So maybe you're thinking, how can you write these experiments and not even know whether they work or not? Well, it's part of the fun, isn't it? I think there are some layers happening there, people. It's not quite exactly what I was hoping for. It's a little bit dark. I think there is a little bit of mixing happening in, but definitely, there is definitely a red, dark red layer and it looks like a black layer. Okay, tip that out, tip him out, and we need to give it a little bit of a rinse. So rinse out the green. And this time we're going to make up a solution with 3 spoons of sugar. So a little bit less dense. A little bit less dense. Now there is I have done this similarly with different sweetness liquids like honey and glucose and sweet water and stuff like that. There is something called density towers. So 5, 4, 3. Okay, 1, 2, 3. Stir him up. Dissolve him. And we're going for yellow now, aren't we? So I this glassware, don't you, in a stirring rod? Don't bang it though, because you might break the beaker. I wonder how many of you have already broken a beaker. Hopefully not many. They are very robust. But we might have hundreds, if not thousands, of kids who do this course. So if you've got thousands of kids, if there's thousands of kids doing this course, eventually someone's going to break a beaker. Hopefully it's not you. Hopefully it's me. And a little bit of yellow. Let's get a nice, I know the yellow, there we go, yellow. And now I'm all nervous again because I don't know whether it's going to work. Okay. Dribble it in, let's see what happens. Sort of. I can just sort of see a yellow layer on top. So it does go red, a darky colour, and then a fainter yellow. Maybe. And the final one is a blue layer. Now, we're not going to add any sugar at all to that. So the final one is a blue layer that we're not going to add any at all. So just get some water, get some blue. That's probably a bit dark. I'm going to lighten that up a bit. And let's see what happens. Well, I'm getting a green and a yellow because the blue is mixing with the yellow. Okay. You know what? It's not a complete disaster. It's only a partial disaster. It's not complete disaster. I think we should leave that for a while. That's what I think. Even if we were to leave it overnight, it might be very interesting to see what happens. So, yeah, I'm going to leave this in the worksheets, which is obvious because that's what you've got in front of you now. Like, obviously I could change it now because they haven't been sent out yet and I can edit them, but no, I'm going to leave it as is, as in the worksheet, because I'm satisfied. That is satisfactory. I can see a red, a darker colour, a yellow, bit of a green, and a bit of a blue on top. I wonder how this would work with salt. I really do. How would it work with salt instead of sugar? Well, why don't you find out? Love it. So let me pop that over here just to rest, I guess, and see what happens over time. All right, now I'm going to do a little bit of mathematics. Okay, mathematics. Now don't freak out and say, oh, I can't do maths, I hate maths. You know what? Maths is actually a really great subject. Okay, maths really is a great subject. And what we're going to do is we're going to get an empty beaker, and the question we're going to ask is, what is the actual volume of an Orbeez? What's the volume of an Orbeez? Now, 1 milliliter is 1 centimetre cubed. So a centimetre by a centimetre by a centimetre. You think I think that's less than a centimetre cubed. So I think the volume of an Orbeez's got to be less than a centimetre. That's what I think. How do we actually work out the volume of an Orbeez? Well, I'm going to show you. We're going to use what's called the displacement. No, we're going to use what's called fill the gaps. That's what we're going to use. And so I'm going to put 1. We have to count them. 2. Goodbye, Orbeez. 2. Let me tip some into my hand. 3, 4, 5, 6, 7, 8, 9. Now, what's very, very important is that you don't go over the 10 mil line. So I've actually got to get that one out. The last one I have to get out. Got him. So I have got 8 Orbeez, and they're under, I'm just pushing them a little bit, they are under the 10 mil mark. Okay, the 8 Orbeez are under the 10 mil mark. So that number, the number of Orbeez under the 10 mil mark is 8. So I need to write that down. Okay, so the number of Orbeez under the 10 mil mark is 8. And then, but there's lots of gaps between them. What I need to do is, I need another beaker. Oh, this is the beaker that I wanted to use. What's another way of doing it? Okay, another way of doing it is actually to use the markings. There's actually markings on this pipette, but they're a little bit difficult to see. This is a 2 mil pipette. Not particularly accurate, so that's why I don't want to use it. But, oh no, I'm going to have to destroy this experiment. You have to redo it, okay, because I need the beaker. I need the beaker, that's the problem. And so I'm going to fill this one up to exactly 10 mil. And I'll just put a tiny bit of food colouring in it. 1 drop. And it needs to be at the 10 mil mark. So let me bring that up. All right, good. Now empty the pipette. We're going to see how much water is required to fill the gaps. So how much water is required to fill these gaps? See how the gaps are getting filled? In goes the water. And I'm bringing up the water line to the 10 mil mark. Now we don't want them to float. Okay, that's the last thing we want them to do. Everything has to be under the 10 mil mark for this to be accurate. There's a tiny bit of flowage happening there, but not much. That's the 10 mil mark there. So, how much did I add? I added 6 mil. I added 6 mils. There was 6 mils of gaps. So, the amount of water needed was 6 mil. So what is the volume of the Orbeez? It's 10, that's the original 10, minus, okay, 10 minus the amount of water we needed to fill it up. So it's 10 minus 6 for me, 10 minus 6, which is 4, and divide it by the number of Orbeez, which is 8, which gives me 0.5 millilitres per Orbeez. There we go. So the volume of an Orbeez is half a milliliter, okay, or half a centimetre cubed. Isn't that interesting, right? Isn't that interesting? So, I do like science and I do like maths as well. Now the Orbeez grow by absorbing water. The Orbeez grow by absorbing water. Now, if we put them into, so that means they're the molecule, and it's a polymer. It's a long chain molecule that's absorbing water within its molecular structure. If we put the Orbeez into salty water, okay, if you put the Orbeez into salty water, so I'm going to make that quite salty, and I should dissolve this water. We're going to have a go at dehydrating the Orbeez. Dehydrating remains to remove the water from them. Okay, and if you remove the water from them, they should shrink. Okay, they should shrink with time. And so I've got that dissolved, and I'm going to put a couple of Orbeez in. Okay, whoop, whoop. And I probably should label. I probably should label this beaker salt, okay, salty water. And I'll leave that overnight and see what happens. Now, it's good to have what we call a control. What's a control? Well, a control is control is, what would happen if I leave them overnight in just plain water? That's an example of a control here. So if I leave the same number of Orbeez, okay, overnight next to it in plain water, then I can see what effect the salt water has on them. Now I really should have them the same height so that it's sort of everything sort of fair. There we go. So we've got salty water and plain water. This plain water is running to the control. It's going to show you what happens to the Orbeez when there's no change. This one's going to show you what happens to the Orbeez if they're in salty water. Now, you can also try sugar, you can try bicarb soda, you can try, oh, I've actually got water there, or citric acid, okay? Will those other chemicals dehydrate? And you'll know they're dehydrating because they'll get smaller and smaller and smaller. I do love Orbeez. Hopefully you love Orbeez now as much as I do. So much to investigate with Orbeez. They will dry out over time. That's why I didn't mind them rolling around and that sort of thing. They'll dry out over time. But maybe don't have them around for the dog to lick up and stuff like that. They're relatively non-toxic. But if someone or something does swallow it, I guess seek medical advice would be my recommendation. Okay, well, hopefully you've enjoyed this lesson. And I'll look forward to seeing you again soon. Bye for now. Hey. So in this lesson, we're going to be exploring fake snow and magic mud. You'll need the junior chemistry set, of course, some food colouring. You'll need some artificial snow, fake snow, and some citric acid, some salt, and some corn flour. So the very first thing is we're going to look at some snow, fake snow, and the question is, where did the water go? Where did the water go? So without further ado, let's get out a 10ml beaker and a spoon and our fake snow. Now just check to make sure that your spoon is dry. I'm not drying it on my shirt. Maybe I should dry it on the bottom of my shirt. Make sure it's dry because that way the chemicals won't get stuck inside it. Okay? So I'm just going to use a corner of a cloth to make sure it's nice and dry. Beautiful. And we're going to get a spoon. Now when we open up this vial, what I like to do is like to give it a little bit of a flick, just so that the chemical settles. And then I twist. So it just pops off gently, because if it pulls off really hard, everything might go flying everywhere. And then pop in the spoon. You could pop in the spoon, or you could actually like tip, like tap, 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 tap. That's another possibility. A little bit of tapping to get the chemical onto the spoon. Tap, 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 tap. And what's best is a level spoon. A level spoon. And I'm just going to do some more tapping just to get it perfectly level. And then I'm going to put my lid on straight away so that if I bump over the container, it won't like go everywhere. Let's pop the spoon of fake snow, and that all went in, which isn't really good. And let's just get some water in another beaker, and I'm just quickly fill up the water like that, super fast. And then a little bit of food colouring, of course, because food colouring just always makes everything better. So I wonder how much water is absorbed by the fake snow. Let's find out. And so, oh, just squirted water everywhere there. You know, we could, I'm just going to give it one. There we go. That's a big squirt to start off with. Whoa. And I've got my stirring rod, and I might give it a stir. And let's see. Whoa. Yeah, it's thickening up. Look at that. It is. Whoa. It's absorbing it. That's for sure. Now I will give you a little bit of a warning. Make sure there's no like salt in the water or in your beakers or in your pipette. Fake snow doesn't really like other chemicals. Oh, look at that. All that big squirt of water is now totally absorbed. In fact, that snow feels quite sort of dry and fluffy, so it probably means it can actually absorb more. Sodium polyacrylate. Sodium polyacrylate. That's the technical name for it. What about if I give it another squirt? Now what I probably should have done is actually started off with exactly 10 ml and then transferred water to the fake snow, and that way I could actually see exactly how many milliliters of water one tiny spoon would absorb. I quite like that. I think I'm going to just sort of leave that like that. If I add more water, and you can add more water, we'll go slushy. Well, yeah, let's keep going. Let's keep going. Because if it goes slushy, what we can do, we can always add a little bit more fake snow to it, can't we? Not fake, yeah. Well, we can add, if it goes slushy, we can actually just add some more fake snow. Look at this. I'm really loading it up. And I think it's absorbed as much as it's going to absorb because it's sort of like a bit slushy now. Looks like one of those slushies down at 7-Eleven. So I might just get the fake snow and just do a little bit of a tap, 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 tap. I'm not going to put much in. Just a little bit. And if I mix that in, that will actually, there we go, that's actually going to absorb the, absorb the rest. Now, it can get quite messy, fake snow. That's okay. Now, I'm going to make some yellow fake snow. I might just tip that in there like that. And whoop, get some yellow. I don't want that tingy blue. I'd like to have just very clear, colourless water. Excellent. And add a bit of yellow. Nice strong amount. Very concentrated, I should say. Add some tap, 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 tap. It sort of sinks, so it is denser. It is denser than the water. And mixing it up. I've got a feeling that this is going to overflow. Is it thick? I can sort of feel it thickening up a little bit. Yeah. Might add a little bit more. Let's see what happens, eh? Takes some time. I don't think it takes a lot of time. Yep. 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 Here we go. Thickening as that sodium polyacrylate absorbs the water into its polymer structure. There we go. Oh, I think it might even start overflowing. Now I wonder what happens if we actually combine different coloured snow. So I've got like yellow and blue here. Ooh. Look at that. And I need another container, so let's use this container, the big plastic container. Put some yellow in. Like this. Let's add some blue. Oh, this one's much fluffier. Mix him up. Blue and yellow fake snow make green fake snow. I like it. I like it a lot. I wonder what other different colours will mix together nicely. So, what can I do anything to get rid of this snow? Well, glad you asked. What about if we add a little bit of salt? Add a little bit of salt to the fake snow. Now, if I've got a big bag here, I'm going to tip some out, attempt to tip some out onto this white plate. Whoop! You'd think I'd get better at that. I just get worse at it, don't I? What a mess. And I'll get my spoon. Let's pop a spoon of salt. 2 spoons of salt. There we go. 2 spoons of salt into the snow here, and I'm going to give it a mix. And I know when you add salt, something interesting happens. Uh-oh! Uh-oh! It's liquefying. Yep. The salt will liquefy your fake snow. Now, it may look like it's melting. It may look like it's melting, going from like a solid to a liquid. But melting actually requires heat to be absorbed. The application of heat causes melting. Now, this is actually what one would call just liquefaction. Okay, liquefaction. It's not heating it. So look at that. Somehow the salt has caused the fake snow to liquefy, which then begs another question. Is there another chemical that we could add? What would citric acid do? Does citric acid do a similar thing? So tip in some citric acid. And I literally don't know. I've never actually done this myself. So I'm doing this for the first time ever. And as I stir it, yeah, interesting. Citric acid is liquefying it as well. It's going quite cold as well. It's very endothermic reaction there. In fact, I'd actually say that the citric acid is dissolving that faster than, not dissolving, liquefying that faster than the salt. I wonder what other chemicals might do that. I wonder whether sugar would have the same result. I don't actually think it would, to be honest. But I've been surprised before, and I'm sure I'll be surprised again. And sometimes the only way to find out is to try it. So that's my challenge to you, to actually go and try it. So here I am doing the washing up. And tip it out like this. And I think you can even like do a bit of scrapey. Look at this, see? Scrapey, and I think I've got a little cloth here. Great idea to like just keep things a bit tidy, a bit clean. This is a total disaster. Well, yours is probably quite messy too. But the beauty is, with a little bit of effort, we can clean up. And you know, it is a good thing to keep your, whatever you're doing, it's a good thing to keep tidy and organised. Unless you're one of those creative geniuses that needs a bit of mess everywhere. And now it's not mess everywhere. What it is, it's actually like things that you might need are readily available to hand, which is a little bit like my workshop. Looks like a total disaster, but it helps inspire me when I'm looking for something to make. All the parts are sort of here. So that's my excuse anyway. It probably would be easy if everything was like set out in boxes and stuff like that. And a lot of it is. But a lot of it is not. Anyway, so we're nicely cleaned up there. And I wonder what would happen. I wonder what will happen. And again, I haven't done this yet, so you're probably thinking to yourself, Jacob, do you try anything before you come on these like lessons, or are we just like the guinea pigs and we're exploring as we go? Well, that's probably closer to it. You're probably closer to it. Now, why did I say guinea pigs? Because some of you have probably got some pet guinea pigs. Well, in the old days, scientists used to test, medicines and things like that on little guinea pigs. Now, don't cry, because guinea pigs are not as important as human life. And so, if a guinea pig had adverse reactions, died to something, that's much better than a person dying. And so, what would happen if I got a balloon? What happened if we got a balloon and we put some fake snow in the balloon? Like this. Now, how do you get fake snow into a balloon? That's a good question. I'm actually going to try the funnel. Now, the funnel does need to be dry for this, because if if the snow gets wet, obviously it's just going to like grow in the neck of the balloon. I wonder if I can put some food colouring in this balloon. Will it go down? Tap, 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 tap. I can feel the snow in there. Yay! So far, so good. Excellent. And a really good thing to do with balloons prior to their use, a really good thing, is to actually give them a good old stretch. Okay? So before you use these balloons, it's good to sort of give them a really good stretch. Like that. And I'm going to put in some water. I'll just get a glass there. And in the water goes. Now again, I have never, ever done this. I'm trying to get this water in. How much water can I actually get into this balloon? There we go. Will it expand or will it... Actually, I don't know what's going to happen. I'm actually like attempting to squeeze in a lot of water. Ta-da! It's very interesting. That feels very interesting. Oh, it's sort of erupting snow out the top there. Ooh. Look at that. I actually didn't know what to expect when I wrote this down. It was like just a little bit of an idea. That is very interesting. There we go. It feels sort of like really rubbery. Okay, little boxing bag. Punch, 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 punch. Fascinating. Absolutely fascinating. This is almost as fascinating as magic mud. Okay, magic mud. Or another name for magic mud is oobleck. Oobleck. And oobleck is an absolutely fascinating substance. And the basis of oobleck is cornstarch. This one says corn flour, but if you see it, get cornstarch or corn flour, much of a muchness. Very, very messy stuff. Okay, incredibly messy stuff, which I'm only going to make more messy by the way that I've opened up. What a terrible way to open up the packet. Like I should have got some scissors. Surely I didn't open up the packet like this, because this is just going to be ridiculous. Oh wow. Kids, don't do it like this. This is, I should put in a little spoon or something. And in fact, this is probably not the best container to do it in. I think we should be doing it in this plastic container. Okay, so there we go. Boop. Yeah, in you go. Perfect. Okay, so no mess here, everybody. Nothing to see, nothing to see. No mess. And 3/4 full, I'd say. 3/4 full. Come on. Come on. You can do it. Here it comes. Yeah, that's 3/4 full. And one moment we've got mess. And the next moment we've got mess. Right. Yay, beautiful. Let's pop that there. Tap, 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 tap. Need some coloured water. Of course we need coloured water. Everything. Woo! What colour? Oh, look, let's go green. I'm going to go green. Good. Oh, that's a strong. That was a lot of green. I'm not sure why I put that much in. And I'm going to use the pipette to transfer some liquid to it. Now, water is a wonderful substance. There's no doubt about it. But in some ways, it's a little bit unremarkable. If you push water, it flows. If you push water, it flows. You can use a pump. You can use a pump to push water. And basically, the harder the pump pushes it, the more it flows. So it's obeying Newton's laws. And one of Newton's laws is that the harder you push something, the bigger the force you push on something, the greater its acceleration. But when you mix it with cornstarch, you get this very unusual substance. And cornstarch is not the most pleasant substance to work with. It sort of squeaks a little bit, not like a mouse, but more like a dry sand. And I need a little bit more water. If you put in too much water, you can always add a little bit more cornstarch. And I'm going for a particular consistency. Sort of that it's going to be liquidy. Okay, so it's going to be sort of liquid. It will look like a liquid. Yeah, it will look like a liquid. But this is good. This is the perfect consistency. If I put in the stirring rod, right, then the stirring rod sinks. No surprise there. So the stirring rod just sinks like in a liquid. But if I bang it with the stirring rod, like bang, 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 then the stirring rod does not sink in it. Or if I try to move it around quite quickly, it sort of tears up like a solid. So I can actually like pick it up like a solid, and then it will actually start to flow. Because the faster you apply the force, the more solid it becomes, the less it actually flows. And so oobleck is actually sometimes called a non-Newtonian fluid, and that is that it doesn't appear to obey Newton's laws of motions. Now, you can play with this to your heart's content. You might even want to make, a bigger amount and, get it in your hands. I've actually used 100 kilograms of this once, and I've made a pool of it, and kids could actually run on it. If you ran on it, bang, 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 you'd stand on it. But if you stood still, zzz, you'd actually sink in it. So, fascinating stuff. And you can keep using it and exploring it. But I'm going to call this lesson to an end, and I look forward to seeing you later. Okay, bye for now. Hey everybody, in this lesson we're going to be looking at chemical reactions. Now basically in a chemical reaction a new substance is produced. Some extras for this lesson you're going to require are some vinegar. Just normal strength vinegar is perfectly fine. White vinegar is probably the best. Nice and cheap. Also, what you'll need is some bicarb soda. Okay, so sodium bicarbonate, bicarb soda. Some, what do we got? Dishwashing liquid. Dishwashing liquid, all right? Doesn't really matter what color or brand, as long as it's a liquid. And some citric acid, which we've used a few times. And, of course, your chemistry set. So, we're going to start by doing what's called a stoichiometric, find a stoichiometric relationship. Let me explain. If you're making a ham sandwich, then you need 2 pieces of bread and 1 piece of ham, because it goes bread, ham, bread. So if you're making 2 sandwiches, that means you need 4 pieces of bread and 2 pieces of ham. Now, what about if you've got 4 pieces of bread and only 1 piece of ham? Can you make the 2 sandwiches? No, you can't, because you don't have the stoichiometric amount of ham for the bread. Or what about if you had 2 pieces of ham and only 2 pieces of bread? Well, one of the pieces of ham goes in the bread and you're still left over with a piece of ham, so you don't have a stoichiometric relationship. And we're going to investigate that with vinegar and bicarb soda. So in your beaker, you need to put in pretty close to 5 ml of vinegar. So effectively, when I say pretty close, it goes 4 ml, 6 ml. So put it on. Actually, put it on the graduation that says, it's between the 4 and the 6. Perfect. So I'll pop that there. And we're going to get some bicarb soda. And I might put the bicarb soda just in the top of this little lid of the plastic round container. And I'm just drying. I'm just drying it because I washed it. Earlier. Oh no, you know what's going to happen, don't you? Maybe. I'm not too sure. Will the bicarb go everywhere? I hope not. Bit tired of the mess. Okay, there we go. So, and then I'm going to get out the spoon, and I might just crush the back of, crush some of those lumps of bicarb up with the end of the spoon. And we're going to start by putting in 1 level spoon. So a level spoon. Now, how do we get a level spoon? We need to use something that's dry. Probably the stirring rod. Well, it's not dry. Mine's not dry at the moment. So again, I'm going to dry it just on the tablecloth. So let's dry him up. And that way the powder won't stick to it. And if I scrape the bicarb off across like that, now I've got 1 level spoon. And that's a very good way to do measurements. And I'm going to pop that bicarb into the beaker, and I get like an eruption. I don't want it to go over. Don't go over, please. I think that was as close as I've ever seen, to be honest. So am I getting a new substance? Absolutely. There was no gas before. And then during the reaction, a gas is produced. And a gas is something. A gas is stuff. A gas is matter. Actually has mass and it has volume. So a gas is matter. Now, the gas in this case, it's not oxygen. It's not hydrogen. It's actually carbon dioxide. And I'm giving this a stir. To make sure that the reaction is finished. Okay, or gone to completion. Now, in this case, the vinegar is a little bit like the bread in the story, and the bicarb is a little bit like the ham. Now, do you think 1 spoon of bicarb was the exact amount to go with the vinegar? Well, what we can do is we find out by, we're going to get another level spoon of bicarb. Okay, so now we get another level spoon, like that. And I'm going to tip that in. And now we've got some reaction again. So clearly there was still some vinegar remaining. All right, so now I give it a stir. And it's still bubbling, it's still reacting. And I'm dissolving it. And helping this undergo a chemical reaction. And I'll know it's finished when the bubbles are stopping produced, and you usually can hear them as well. You can't just see them, you can actually hear the bubbles of carbon dioxide being produced. Alright, so I'm going to call that finished, and let's see if there's any vinegar remaining. Okay, so in goes another spoon, and we're definitely still getting some reaction. We're still getting some bubbles of gas, of carbon dioxide. So far we're up to 3 spoons of bicarb. Okay, the reaction's slower because there's not as much vinegar available. And in actual fact, not only are we producing carbon dioxide, we're also producing a salt, a special type of salt. And I suspect that this might be the final amount of bicarb that yeah, hardly any reaction at all now. So, just a little bit. So I'm going to say that the stoichiometric ratio for this reaction is 5 ml of vinegar and 4 level spoons of bicarb soda. And so if you're doing a giant volcano, whatever, then you could actually use that ratio to get the exact right amounts. And I've done some giant volcanoes before. I've made a giant one out of paper mache. You can actually find it if you do on YouTube, Make Science Fun, and then search for like a volcano or search for Mount Fuji. You'll find that video of me making a giant Mount Fuji. Had to go on the trailer. Had to put this giant volcano on the trailer. I brought it to a school and had big pumps and buckets, and it was fantastic. You should go have a look at it. Okay, so what are we going to do with this newfound knowledge? Okay, because we've got some newfound knowledge now. Well, we're going to actually blow up a balloon with it. So I need to have a balloon. So let's reach into this and get a balloon. And this is quite difficult. This is a bit of a challenge. I might tip out this salty water now and give it a little bit of a wash. Okay, so just squirting some clean water in here to do my washing up. Perfect. And how much vinegar did we use before? We used 5 ml. So I'm going to get 5 ml of vinegar, same amount as before. Tip him in. Whoop, bit more. Whoop. Oh, that was a little bit too much. Of course. No surprises there that I've tipped too much in, is there? Would you expect anything less? Absolutely not. Okay, so I need 5 ml. Perfect. And I'm actually going to put that into my conical flask. So let's pour him into the conical flask like that. Now it looks like water. I mean, it's clear and colourless, but we know that it's vinegar. Next, I need to get 4 level spoons of bicarb into this balloon. Now, I don't have anyone here to help me. The first thing you should do is start stretching your balloon. Okay, so exert a pulling force. This puts it in tension, and it sort of stretches it, and then get the neck of the balloon, not your neck, neck of the balloon, and sort of stretch it as well. That will make it nice and easy. Well, it's not nice and easier, but easier, because this is quite difficult to get the bicarb in. Now, is my funnel dry? That's the first thing I'm going to try. Can I get the bicarb in with the funnel? That's my first question. Let's see. Sort of get stuck up the top. So I'm going to go tap, 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 tap. Now it's disappearing. So I'm actually quite hopeful. If I'm going to be blunt, I can feel that the bicarb appears to have gone into the balloon. So that's 1, 2. Okay, tap, 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 tap. This will cause the particles to go down. Oh, come on. Will you go in? Come on. 2. You've got to make sure that the bicarb is crushed up, otherwise you don't have a chance. 3. It sort of like shot out when I squeezed the balloon a little bit. But it's actually getting there. Look. Whoop, 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 whoop. And my final spoon. Let's get my... So I'm putting in the stoichiometric amount, the correct amount, which we had discovered through experimentation earlier on in this lesson. Wow. All right. Now, what I need to do, make sure I don't have any sharp fingernails. I have to try and stretch this balloon, and I need to try and put it over the neck of the conical flask. Now, if you've got help, you'll be in a better place than I am. I would like to have a third hand to hold the conical flask so it doesn't move away. But I'm feeling confident. I've done it. I haven't torn the balloon, so it is possible to do it, okay, without tearing the balloon. Now, hold the balloon onto the conical flask and then tip the bicarb into, look at this, tip the bicarb into the conical flask. We're getting a chemical reaction. We're producing carbon dioxide gas. That carbon dioxide gas is exerting pressure on the inside of the walls of the balloon, causing it to expand. Look at that. Carbon dioxide gas. Fantastic. Absolutely love it. Make sure you stretch your balloon first though, because otherwise you'll get really strange shapes. So that is chemistry in real life. And also, if you feel the bottom of the conical flask, it's actually quite cold. So yet again, another endothermic reaction. Okay. So did you like that? All right, I'm going to let the balloon go. What will happen? Woo! Bye-bye, Mr. Balloon. And I actually need the conical flask for the next activity. So I'm just going to wash that out as well. Okay, so for the next activity. Because the next activity is we're going to sort of do a bit of an elephant's toothpaste. Now, it's not the absolute classic elephant's toothpaste, which is going to shoot out a million miles, okay? I mean, but it's going to be better. Look, you know what it's going to be? It's going to be the best elephant's toothpaste you've ever done. Almost guaranteed. Almost guaranteed. So for elephant's toothpaste, basically we need to have a whole lot of bubbles, and those bubbles need a whole lot of gas produced, and that has to blow up bubbles and go through some food colouring. So toothpaste, let's say Colgate's got those red and blue and white stripes, and elephants are big, and so elephant's toothpaste is like this foam that comes out that's like striped red and white and blue. That's what elephant's toothpaste is. And so what we need to do is get some bicarb soda into this conical flask. That's the first step. Now, how much? Well, again, we could use that stoichiometric amount, okay? But we actually want it to react fairly quickly. That's as well. So I don't actually mind doing a little bit extra, okay? It's okay to do a little bit extra. So in we go, and like that, good. And I'll just clean the top of it. Now, I think this might work better if we add a bit of water to actually dissolve it. Okay, so we're actually dissolving it. So this is actually an aqueous reaction. Water's involved, and I think that might speed it up. We really do want this to go quite fast, and so by actually doing in water and not having the powder, I believe the reaction will go a lot faster. And we need something to hold the bubbles. And so in this case, detergent's going to hold, well, it's not going to hold them like this, but it's going to help stop them from popping. And I don't think we need too much. Okay, so give it a good mix like this. Mixy. We got some good detergent in there. And then we need our vinegar, which we're going to pour in. And so let's put in some vinegar in here. Just in a beaker, so that's easy, quick and easy to pour in. Lovely. And finally, we need our colours. Okay, we need our colours. So remember what colour I said? I think I said Colgate was like... Now, this video is not sponsored by Colgate. Okay, just to let you know. There's no, like, product placement and all that sort of stuff. And a bit of red on the other side. Lovely. Are we ready? Yes. Are we steady? No. Okay. Ready, set, go. Here we go. And we've got the bubbles. Woo! Look at that beautiful purple coming out. Oh. A purple tower. I think that was somewhat satisfactory. Certainly wasn't what I was sort of hoping for, I'll be perfectly blunt. I mean, I'm enjoying it. It's travelling now. And this foam here is actually closer to what I expected. It's still bubbling out. I think there's quite a few different changes that you could do to this. What would happen if we didn't dissolve the bicarb powder in the water? Would that make a difference? What about if instead of having the detergent in here, what about you actually put the detergent with the vinegar? What about if you didn't use detergent at all? These are all important questions. And what about my new favourite chemical, citric acid? What about instead of using vinegar, you actually use citric acid? And you could actually blow up the balloon. You can actually blow up the balloon by putting... Well, let's do that. Let's do that, okay? I want to show you how much I love citric acid. So I have to give this a little bit of a wipe down. And this one here is not going to be that easy to clean. Oh, no. No. What a mess. What if I put squirt the water up into it? That might help a little bit. Lots of water. This is probably where you need to bring this to a tap. I think we might get there though. What about if I just like tip it in crazy like that? And tip a little bit out, put the rubber stopper on, and give it a shake like this. Shaky, shaky, shaky. This will help rinse out and I can feel it all. It's all very soapy and very slippery, and that's because of the detergent, of course. Oh, I think I'm having some success here. A little bit of, you shouldn't put your finger on the end and shake it, because it's okay for this experiment, but in the future you might actually do it with some more nasty chemicals and you might end up with a little bit of a burn or something. So try and get in the habit of not touching chemicals. Okay? Safety first is a great motto. Okay? A great motto. Boy, that detergent is really quite residual. Anyway, let's pop it there. And this time, we're going to check out the efficacy of the bicarb and citric acid. Now, I'm actually thinking, in this case scenario, I want to put the bicarb into the conical flask. So, there we go. In you go. In goes the bicarb. Lovely. Didn't really measure it this time. I think it needs a bit of water. Okay. So give it a bit of a mix there. And actually, there's a little tiny bit of a reaction happening there, which I'm a bit surprised by. And I'm going to get another balloon. And remember, stretchy. Okay. If you give it a good stretch, it will be much, much better for this experiment. Here's my funnel. Pop the funnel down. And I'm doing this a little bit what we call bucket chemistry. And bucket chemistry is when you're not really focusing on exact quantities like stoichiometric quantities. We could work out how much citric acid is required how much citric acid is required to react with a certain amount of bicarb, we could certainly do that. Okay? I just don't feel like doing that right now. Maybe I just want to actually see whether it works first. That's often what I might usually do. I'll just see whether something works before I go into any great depth. So, yeah, I've got a little bit of citric acid there. I might just try and pour in a little bit more, like this, straight into the balloon. Straight in. That got some more in. I think that will do it. I think that will do it. So again, you know what? I might just add a little bit of food colour. I'm not too sure why I'm doing this, but I am. There we go. And then I have to try and get this balloon stretched over the neck. So stretch. Oh, I can feel crystals of citric acid inside the inside of that balloon. And over. Yes, I've got success. And let's try and get that citric acid in. Okay, come on, citric acid. Do your thing. Yep, here we go. We do have some citric acid in, and I'll give this a little bit of a swirl. This will help dissolve the citric acid. I've got foam. I've got foam going up into the balloon. Can you see this? Look at this. You can see the foam traveling upwards. And there's foam. Look on this side. There's actually foam in the balloon. Woo! Whoa! There we go. Squeeze that up. Up there. Push the gas up there. Look at that. It's almost an artwork. Dun, da, da, dum. Beautiful. What a pretty as a picture. I'm pretty sure I'm not sure whether I needed more citric acid or more bicarb soda. Who knows? Well, you can actually do an experiment to find that out. That's it for this lesson. I look forward to seeing you again soon. Bye for now. Are you as upset as I am that this is the last lesson for the Junior Chemistry Set 1 course? But I've got some good news. There's a Junior Chemistry Set 2 course! Yay! And with the Junior Chemistry Set 2, there's fire. Oh yeah. So, in this course, we experimented with a lot of different substances and a lot of different particles and dissolving and some chemical reactions. In the second course, we're going to be looking at a lot of heating and cooling. Heating and cooling. And in order to heat, one needs some fire. And so Tiny Science Lab has developed a relatively safe way to heat liquids. And we use this special little tripod that we've made and a little candle, and we're actually able to, here we go, heat up our substances. And so we can cause different substances to change state. We can look at the rate of heating. We can look at the rate of cooling. We can see the effect that heating has on different substances and bring about different chemical reactions. There's so much more that we can explore with our Junior Chemistry Set 1 and in combination with the Junior Chemistry Set 2. So I really hope that you're as excited as I am. But in summary for this course, what have we found? Well, we've found that all substances are made up of particles. So for example, the water in this beaker, we can represent it as little tiny particles, and those particles are moving around. And if we put in some food colouring, we could actually represent that with other coloured dots. and if it was concentrated, we'd put a whole lot of other coloured dots, or if it was dilute, we'd put fewer dots. Now, there's some substances, like salt, that when salt dissolves, it actually breaks up into the sodium and chloride ions, and that's what dissolving is. However, when sugar dissolves, sugar actually dissolves up into like the molecules of sugar. Some substances are made of what we call charged particles, and some substances are composed of molecules. And as you explore and study chemistry further, this will make more and more sense. And we looked at things that were floating and sinking. Now, things that were floating and sinking, their particles, well, if they were floating, their particles are less dense than the substance that they're floating in. If they're like neutrally buoyant, their particles will be about the same density as the thing that they're in. But if they're heavy, like a sinker, the particles will be packed together and will be very, very dense. And there's a good reason why some things float and some things sink. Now, if you've got cold water, then the particles are not moving around very fast at all. The particles are going really quite slowly. But if you've got hot water, those particles, they're going to be moving around quite quickly, and they're going to be bumping into each other, and they're going to be bumping into the walls of the container, and those collisions are going to cause things to happen. And that's why in the next course, when we investigate heat, we can actually make other chemical reactions happen by using this principle of heat, where the particles are going much, much faster and can cause collisions and cause things to happen. And if you trap some of the particles in like the conical flask, well, those particles, they can't leave. They bump against the lid, they bump against the walls. It's called pressure. And if you put in more of those particles, like when we blew up the balloons with our chemical reactions, well, if you've got more of those particles, then there's more and more collisions on the side of the inside of the balloon, and that causes the walls of the balloon to expand, causing the balloon to get better. Not better, well, it is better if you want it bigger, that's for sure. And so that's why we were able to blow up the balloon with the chemical reaction, because the chemical reaction produced gas, and that gas went into the balloon, and those particles, because there were so many particles, they collided with the balloon, causing it to push out and push against air pressure. So congratulations on getting through this entire junior chemistry set 1 course. What an achievement. I hope you're feeling, quite chuffed with yourself, because, it was a lot of work and a lot of videos to watch and a lot of chemistry to do. But I hope you had fun. I hope you had, that you learnt lots, and I hope that you're inspired to learn more. Because as you get older, like me, you'll actually be able to apply the things that you've learned to real life situations, and not only that, it will help you understand how this wonderful world works and interacts, and you'll be able to interact more positively with it. You'll be able to make the world a better place. So I look forward to seeing you again in the next course, in the Junior Chemistry Set 2 course. But until then, stay safe, and I'll see you later. Okay, bye everyone. Thanks so much for doing this course with me, and I can't wait to see you again. Okay, bye-bye, 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 bye-bye. Bye everybody.